Okay, I should be live. Hello, can you hear me? Let me know in the chat. Good evening, or if you're in America, then good afternoon, I guess. Or if you're in Australia, then good early morning. But yeah, I don't expect that anyone from Australia is watching right now. Yeah, hello, and yeah, let's start, I guess. Only I'll wait for you to let me know if I'm audible. Yeah, audio all good. Okay, great, thanks. So yeah, hello. Whom have I seen in the chat? I saw Real Cygnus before. So if he's still here, then hi Tiny Captain, hi PT. Oh, sorry, my cats are making some mess, so I might be looking over my shoulder every once in a while. Okay, right. So, what am I going to show you today? So I'm going to show you a bit, well, a good deal actually of maths that's behind my simulator. If you've seen the video part 1, then you know what this is about. There is this simulator I've written some time ago. It's basically to simulate views from different places all over the world with the Earth being assumed to either be a globe or flat, although it got a bit more complicated, but I'll cover that in a while. Yeah, and then we can see which of the generated panoramas, if any at all, fit the photos better. And if they do, then it's nice, right? Because we can say that, okay, so this model fits reality better. I'm not sure if you're hearing that, but yeah, my cat started digging, so you might be hearing weird noises in the background. Anyway, right, so we'll be covering how this simulator actually does what it does from the mathematical side of things. So from like general overview side, that was the first video, which I think I've linked in the description, so you can go check it out. Well, probably you'd have to disconnect right now if if you wanted to do that, but anyway. Right, so this stream is going to cover quite a lot of stuff, and yeah, it would probably make sense to divide it into parts somehow, but yeah, I'm going to try to do it all at once, so we'll see. But I'll try to basically to point out which parts start where in the description afterwards. So if you're watching this from a recording right now, and you're wondering about some specific part of the stream dedicated to some specific part of the simulator, you should be able to find timestamps in the description below. But yeah, if you're watching this live, you obviously won't, because that hasn't been recorded yet. Okay, so let's start with the main parts of the simulator. Let me switch to showing you my screen. I should have probably prepared some slides or something, but since I didn't, I'll just draw in real time. Okay, let me also check out my notes. Okay, so maybe I'll pop that over to a different screen. Okay, I guess that will work well. Oh, we have Cinnamon Control. Hello, nice to see you here. Yeah, so maybe I should also mention that actually this whole material, the first video and this part about mathematics behind the simulator, is partially inspired by a conversation I had with Cinnamon Control on Discord. So he actually expressed interest in seeing how all of this works. I had an idea for doing that before, but I never really could get motivated enough to actually record something. And he kind of gave me some more motivation, although that was a long time ago actually. I think that it might have been almost a year, at least half a year, probably. So yeah, I still took some time before I actually recorded this stuff, but hopefully this will be useful. Anyway, so yeah, what I wanted to say now is that the simulator has, let's say, 6 main parts, which I'll be covering. And I'll be covering them in roughly the order I will be presenting them right now. So first and foremost, the most central part of the simulator is, okay, let me just write it here. Okay, so the most central part is the refraction model. So obviously, since it's called, well, I'm calling it often refraction simulator, it has to incorporate refraction, and actually that was one of its main purposes, to incorporate refraction both on a globe and on a flat Earth, so that we could have like more precise predictions of what we should see on both models. So refraction is quite important, and yeah, it's pretty much the central part of this whole simulator, but of course, since it needs to do some more stuff than just simulating how light rays are bent, there are many other parts. So the second part is the Earth shape model. So let me write it just here. And these are related because the refraction model, actually the equations that the refraction model uses depend on what Earth shape model is assumed. So the equation that is being used is slightly different on a flat Earth than it is on a globe. We will see in a while why that is. Well, it's justified. It's not just something I pulled out of who knows where. So these are connected actually. Then there is the atmospheric model, which is also quite important because atmosphere is what causes the refraction, right? So we have okay, I'll just look if I'm writing where you can see it. And the atmospheric model is obviously also connected to the refraction model, because this is basically what determines what index of refraction is at what altitude, and this is an input to the refraction model. So then once the refraction model knows what index of refraction is where, it can calculate the path of the light rays. Yeah. Okay. So this is pretty much the physics. This pretty much covers the physics behind the simulator. There are also three, let's call them auxiliary parts. So there is something I just called temporarily a viewport model. Sorry. So what this is about, so that's basically that determines, okay, that's not really related to the refraction model, it's separate. So this determines how pixels in the image are mapped to directions in space. Because basically, as I've covered in the first video, if you look at how image is created either in the eye or in a camera, then you realize that every pixel in an image, like in a camera image for example, corresponds actually to a direction in space. Different pixels correspond to different directions, so there needs to be some kind of mapping between the pixels in the resulting image from the simulator and actual directions in space, and this viewport model takes care of that. So you would think that there is a single most correct mapping, and in a way you could say that. So that would be what corresponds to a rectilinear lens in a camera, where if we have straight lines in reality, they should be mapped onto straight lines in the image, but it gets a bit more complicated, and actually the first model I implemented wasn't the rectilinear model, it was a different one, but what was it and why that one was implemented I'll cover when I'm talking about the viewport model. Then there is the terrain model, so we need to have some terrain. So we need to figure out, in order to even generate a panorama of I don't know, actual mountains or basically actual geographical features, we need to have some data about what is there in the world, right? What is the terrain elevation in different places. So there is a whole part of the simulator dedicated to that. And well, when the simulator creates the image, these parts actually interact, so the refraction model takes care of of basically how the ray is bent and how it travels through space, but then at every step of calculating the ray, the simulator needs to check if the ray intersected the terrain or whether it didn't. So if it intersected the terrain, then we have a hit and we know how to color the corresponding pixel in the image. If it didn't, we just continue propagating the ray until some predefined limit. So that's the interaction, but I won't draw an arrow here because, well, those are really still two separate things. I mean the way the ray travels in space isn't really affected by the terrain itself, so these are not connected that directly. It's more like the part of the program that tries to generate the image needs to use both of them in order to generate the image, basically. And then there is the last part, which I'll be covering in the end. It's coloring. So whenever a ray hits the terrain or some object, because at some point I also introduced the possibility of defining some custom objects in the scene, like cylinders or textured billboards. Basically those are the only two right now in the simulator. It's an option. Well, I might introduce more in the future, but currently it's just these two. So whenever a ray intersects either the terrain or an object, we need to color the pixel somehow, right? We know where it hit, so the program knows where it hit, the geographical coordinates, what has been hit, whether it was an object or terrain, what elevation, like stuff like this. And it needs to somehow choose a color for the pixel. So in reality, the color is simply determined by the properties of the material of whatever the ray hit. But here in the simulator doesn't go as deep into simulating stuff. So for the terrain, the only data that we really have is the elevation. And yeah, we need to work with that somehow. So the coloring I have actually uses that and some additional data. And for objects you can actually define the color that the object should have. So the simulator can use that. But yeah, so that's it. Those are the parts I will be talking about today. Starting with the refraction model, then we'll go to the Earth shape model, then we'll go to the atmospheric model, then I'll talk a bit about the viewport, the terrain, and the coloring, but the main part, the really meaty part that has a lot of maths and a lot of physics behind it, it's pretty much these three. And, well, maybe the viewport model a bit, but it's more geometry than physics, and it's not that much of it. Oh, I see we have Dora. Hello. Nice to see you. Okay. Right, so let's go to the refraction model. So let me consult my notes, what I wanted to tell you about it. Okay. So the first thing I want to tell you is that, okay, so all of this whole program, this whole project of the atmospheric Raytracer actually started as a much smaller thing. So it started as something I called the refraction calculator. It was a simple program that simulated just a single ray, and what it did was it could take as input the initial altitude above the sea level of the ray, the angle at which the ray starts. So basically you could decide whether it starts horizontally or slightly upwards or slightly downwards. And then it could calculate the path of the ray and output, for example, at what elevation it was at some distance from the start. So that's basically it. It had no idea of any terrains, it had no idea of any viewports, colorings, because it didn't even calculate any pixels. It had a really vague idea of the Earth shape, because even then it was intended to show the differences between the globe Earth and flat Earth. So basically you could specify if the Earth was supposed to be a globe or flat, and those were the only two possibilities. And the atmospheric model was very rudimentary, and it basically just assumed exponential. So if I write this as an equation, maybe, so if we have if we have the index of refraction, which is usually denoted n. So for air, it is often something along the lines of 1.00, I don't know, I don't remember how many zeros, I think 3, and then something like 2, 7, and something. So that's the index of refraction of the air. Of course, it varies slightly with temperature, with pressure, and so it also varies with altitude on Earth. But the point is, this part after 1 is very small, and that's basically what's changing. Well, the index of refraction can't really fall below 1, because it would mean that the speed of light in the material, in the medium, is larger than the speed of light, because this index of refraction is basically just the factor by which the speed of light in the medium is smaller than the speed of light. So if the speed of light in a medium is twice smaller than the speed of light, then this index of refraction is 2. If it is 1, then it means basically we're in a vacuum, and the speed of light is in the medium is speed of light in the vacuum. There are some very special cases where the index of refraction is, for example, negative, but I won't go into that now. There are some very, very weird situations in which that's possible. So, what's happening? My cat is talking. Okay. Anyway, so the thing is that the initial model of atmosphere was basically just that the difference between the index of refraction and 1, so basically this whole part after the comma, was some index of refraction at 0 altitude minus 1 times basically an exponential function, so something like this, where h is the height above the sea level, alpha is some constant, e is 2.718 something. It's the famous constant, the basis for the natural logarithm. Yeah, and so that was basically the initial model for the atmosphere. It got a bit complicated in subsequent versions. Oh, that's what I should say. Right. But still, it needed to have some notion of how the index of refraction changes with altitude. Anyway, so for this I actually have a document. So for the refraction model that I'm using, I actually have a document which I prepared once, and I will show you right now. Let me open it. So yeah, a while ago I prepared the PDF, which I actually already linked in a few places, which details how I'm calculating refraction. It's exactly what I'm using in the simulator, so we can just briefly go over it, because that's I basically wrote down all the calculations here, so I won't write them down again. So basically, what I'm using is such a weird coordinate system, where the altitude is h, and x is distance along the surface. So if the surface is spherical, then this x-axis is curved because it's along the surface, so it might look a bit weird at the first glance, but it's actually a perfectly valid coordinate system. It's, for example, if we are using a polar coordinate system, then, for example, this one axis would be the radius, the distance from the center, and one axis, the second coordinate, would be angle around the center. And it's very similar here, actually. This x is pretty much like the polar angle in the polar coordinates, only it's scaled by the radius, right? So the distance along the surface, if we move by some angle phi, then if we multiply it by the radius of the Earth, then that's the distance along the surface. So that will be the coordinate x, and h is just radial coordinate with the radius subtracted, so it's just the altitude above the surface. Why did I choose it so? It's because then if we imagine that we change the radius of Earth, this big R, capital R, then we can imagine that it would straighten out slightly, and if R tends to infinity, then we would basically get a rectilinear coordinate system where h is along one direction, x is along the second direction, and they are perpendicular to each other and both are straight, and that would correspond to the flat Earth. So this way I can just derive the equation once for some arbitrary value of r, and then consider the limit of this equation with r tending to infinity, and then I will automatically get the solution for the flat Earth. So that was basically the idea here. Yeah, and as I write here, we only assume the refractive index depends only on the altitude. Oh, we have Gary Waibenga, hello. And he's writing that mathematics is not reality. Yes, we all know that. We all know that mathematics is not reality, but mathematics can be used to describe reality, and that's what we're doing here. Okay. So now what I'm writing here is the length element in such coordinates, and it's like this. So what does it mean? It basically means that if we take 2 points and their h coordinates differ by this dh, and their x coordinates differ by dx, and both are small, in the limit infinitesimally small, then the distance between these 2 points squared is just the difference in h coordinates squared plus the difference in x coordinates squared times this factor. Now, why something like that? Well, basically, if we look here, okay, I might try to give me a moment. I will try to launch a program. Okay, now I don't remember. Okay, F9. So now if I do this, I should be able to draw. Okay, perfect. Okay, so if we look at, for example, this segment, and if we look at this segment, then both subtend the same angle at the center. If we extend those lines to the center, then the angle here will be the same, right? It will be the same angle, let's call it phi. And so the length of this piece will be r times phi, and the length of this will be r plus h times phi, where we consider the h to be here, right? It's some altitude h. Okay, so if okay, so now if this is like delta phi, it's like a difference in some angle, right? So it's like an angular difference between those two positions. It's the same here and it's the same here, and so this change of x coordinate, this delta x, which is along the x-axis, is r times delta phi. But the actual distance between those 2 points is this times, again, delta phi. And if we try to extract the x, delta x, it will be r plus h divided by r times r delta phi, which this is delta x, right? Which means it's 1 plus h over r delta x. And then if we have delta h somewhere here, then the hypotenuse of this small triangle will be precisely what is written here. Well, if we only substitute d for delta, where d usually means that this is infinitesimally small. So that's where this comes from. And this is actually important because we will need that later in the calculations. And as I'm writing here, it is worth noting that for the flat Earth, this length element reduces to, well, if r is infinite, then this whole part h over r disappears, because no matter how large h is, with infinite r this is 0. And so we just have dh squared plus dx squared, and that's, if this wasn't called x and h but x and y, it would be the same as dx squared plus dy squared, and that's exactly the same as in normal rectilinear coordinates x and y. Okay, Oh, hello, truth nerds, and yeah, I have a drawing tablet. I bought one since when I started recording videos for YouTube, because my first videos were already where I was writing some maths, and I decided I needed something to quickly jot notes during recording. So I just bought some kind of a simple tablet, and it's fairly useful. Okay. So yeah, so that covers this part. Let's see if this all disappears. Oh, no, it doesn't. But I want it to disappear, actually. Okay, let's clear it. And let's go to the actual mathematics behind refraction, which is the Fermat's principle. So you might have already heard with regards to refraction about Snell's law. Snell's law basically describes how a ray is being refracted on a boundary between two media. Well, Fermat's principle is in a way equivalent to Snell's law, but in a way it's more general. So it's it's more rigorously, it fits more general cases more rigorously. So in theory, it is possible to derive all of these equations using just Snell's law, but there is one case where Snell's law is kind of ambiguous, but Fermat's principle has no trouble with it, and we will see in the end of this section what that is. So Fermat's principle states that, and here we start with the here we start with the more advanced maths. We have integrals. And Fermat's principle basically states that the integral over a curve, over the path of light, of the refractive index times the length element, well, the path of light is such that this integral is minimal, or more precisely extremal, because in theory it's possible for the path to be such that this is maximal and not minimal, but I think that would be kinda hard to have in practice. Anyway, it doesn't really matter because it's often also written in a different way, and that's what actually is in the miniature of this video, and it's written like this. So this is like a lowercase delta, Greek letter, and what it means in this context is something called the variation. So there is such an idea in mathematics called the calculus of variations, which is in a way level higher than regular calculus. So with regular calculus, like with integrals, with derivatives, we are just concerned with a function, and there might be a function of, for example, one variable when we have variable x, and then y is a function of x, and we have some function, and then we can, for example, calculate the rate of change. We can have more than one variable. We can have, for example, x1 and x2, and then we can have derivatives with respect to both of those, and then a derivative of this function is, in a way, can be thought of as a vector, which points to where to the direction in which the function grows the most. So the vector is then, for example, dy over dx1 and dy over dx2, and such a vector will be a gradient of this function. You can have multiple variables, and a function can also have multiple values. So you can have like multiple functions at once of multiple variables, and then you have a whole matrix of derivatives. Sorry, give me a moment because my cats are basically not allowing me to focus. Just a moment. Alright, I'm back, sorry for that. Okay, so yeah, so basically the calculus, like differentials, integrals, can be done on multiple variables at once, and then it can be thought of as calculus in multiple dimensional spaces, like you have multiple dimension of the space in which the argument of the function is specified, and you can have function from a multiple dimensional space into a multiple dimensional space, and this way you have so this way you have something like stop drawing. So you can have, for example, a function that is, I don't know, from a Euclidean r to the power of n, so n-dimensional space into an m-dimensional space, and then you can calculate derivatives of such functions, and then a derivative is basically a matrix, stuff like this. So variations, the calculus of variations, in a way can be thought of as calculus on infinite dimensional space. And the most basic application, let's say, is for things like Fermat's principle. So in this case, what we really are interested in is, okay, how do I clean this? Okay, so in this case, let's say we have point A and point B, and we are interested in what curve. So every curve between those 2 points has an associated value, and this value is basically this. This is this integral of index of refraction times length. And so this value is different for different curves. So if we choose a different path, like for example this, it will have a different value. A path like this one will have a different value, and a path like this one will have a yet different value, right? And all of these paths are possible, and then we want to choose such a path that has the minimal value possible out of all the paths between points A and B. And it turns out that the set of such paths can be thought of as an infinitely dimensional space in a way. And you can also do something like calculus on it. So if you wanted to find the minimum of a regular function, like you have a regular function of one variable, and it looks something like this. So when you want to find the minimum, you are looking for a place where this is tangent to a horizontal line. So basically where the derivative is 0. That's basically how you look for a minimum in the regular case. With calculus of variations, it's quite similar. You also look for a path for which the variation, as I wrote it, this variation is 0. And how do you do that? I won't really go into details. This has some nice definitions, and this all can be calculated. But the thing is, in such a simple case where we just have a function that when what we want to consider is just an integral over a curve, there is something called Euler-Lagrange equations. It's for a bit more general case really, but it's something that can be used here. And so, okay, let me turn this off. And in a moment I will show you how this can be used. Okay, so here I start substituting stuff. So first, we need to substitute this dl for something that depends on our variables. So, okay, did I already write this? No, I did not. Okay, it's here. The solution will be a path expressed as a function h of x. So we're basically looking for a function h of x, which if we draw in this coordinate space, it will represent the path of our light ray, and we're looking for such a function that this integral, which we will now be manipulating, that the variation of this integral is 0, or this integral is a minimum. So how do we calculate such a thing? So first we need to, as I said, substitute this dl from this length element. So this is basically just this substitution, and we have the square root because this was the square of length, and here we need just length. Now from this we can extract the x, and then we will have dh over dx here, and this will just be the derivative of our function that we are looking for, which we will denote as h dot. So this is basically what is written here. So we have this h dot squared, and the x goes outside the square root. Okay, and so yeah, such a problem can be solved using the Euler-Lagrange equation. That's what I mentioned before. And what do you do here? Okay, so the problems for which this works is basically if you have, okay, let's start drawing again. If you have something like this, and this can depend on x, this can depend on some function of x, and it can depend of the derivative of this function and the x, and we want to find the path for which the variation of this is 0. This is actually a very powerful formalism. It can be used to find stuff like the shape, the curve, okay, the shape of a chain that is hanging between 2 points. So to do this, you're basically looking for a curve that minimizes energy between the potential energy, and you will find this shape. This can be used to find the shape of the path of the least time between 2 points. So it's like a famous problem where you have point A and point B, and this is all under gravity. And the question is, what is the path of the shortest time between these 2 points? Is it just a straight line, or is it something more complicated? Because, for example, if we use such a path, then the object which will move along this path will accelerate quickly at first, and then it will have greater speed at the bottom. So there are many such experiments even on YouTube. You can find them, and you can see how the different paths compare. And you can use this thing called Lagrangian mechanics to calculate what is this path of least time. And yeah, I can see that Truth Nerd says a catenary, so that was for the curve of the chain under gravity. And Real Sinus, oh yeah, he also said cos h or hyperbolic cosine. Yeah, that's basically it. And he's also saying cycloid, so yeah, cycloid turns out to be this path of least time. But yeah, all of this can be calculated using Lagrangian mechanics, and actually this here, mathematically, it's the same problem as this. This is called principle of least action, and it's pretty much the same thing mathematically. Only as instead of like a Lagrangian, which in typical mechanics, like in this path of least time, the Lagrangian is something like the kinetic energy minus potential energy. But here our Lagrangian is something like this. Oh, it's this part without the dx, which is what I'm writing here. And so this is actually a solved problem. So we know what equation has to be satisfied by such a Lagrangian in order for this integral to be minimal. And this is what Euler-Lagrange equation tells us. So the Lagrangian needs to satisfy such an equation. So the partial derivative of the Lagrangian with respect to h, or with respect to the function here, needs to be equal to derivative with respect to x, and of the partial derivative with respect to the derivative of the function, which looks a bit complicated, but it's less complicated than it looks. So let's go further. Okay, I need to turn this off in order to scroll. Okay, so here in this document I just calculate the derivatives. Oh, we have Gentlest channel with us as well, hello. Oh, and I missed Sphera before, if that is how the nick is pronounced. Hello as well. Okay, so this is calculating the derivative with respect to h. So we have h in two places here. We have h here and we have h here. This does not count as h because this is h with a dot. This is the derivative of h, which counts as a separate variable here. So when we calculate the partial derivative with respect to h, we treat this as a constant. We are only interested in the h here and in the h here. So we calculate the derivative. So by the rule of derivative of a product of two functions, so we have one function n and the second function is this whole square root. So we have the derivative of n times the square root plus n times the derivative of this whole square root, which is a bit complex, but if you can do calculus, then you can check that this is the derivative of this whole square root. Okay, so that is the derivative of the Lagrangian with respect to h. Oh, and I denoted the derivative of n with respect to altitude by n prime. So now the derivative with respect to h dot, and h dot is only here, so we need to calculate only the derivative of this square root. N is considered constant here, and so we have this. But now, for the right side of this equation, we need to calculate the derivative with respect to x of all of this. And now we calculate the complete derivative, so everything that depends on x here is considered to be depending on x. So n depends on x because it depends on h, which depends on x. So this will have to be differentiated. H dot depends on x explicitly, and h depends on x. So basically those four terms here are variables in this case. And so we calculate, so this part is just the derivative of this n h dot, so we calculate the derivative of n once, and the derivative of h the second time. No, wait, this square shouldn't be here, I think. Yeah, so that's my mistake, or should it be here? Yeah, I think this square shouldn't be here because I'm pretty sure, yeah. So this part is supposed to be the derivative of the numerator times the denominator, and then it's minus numerator times the derivative of the denominator. So that's the rule for calculating the derivative of a ratio of two functions divided by the denominator squared. Yeah, so this square shouldn't be here, but I think the final equation is correct, so we will see. Anyway. So this looks a bit ugly, but a lot of it simplifies. So we can multiply the numerator and denominator by this square root because we have it here in the denominator in this nested fraction, and we get something like this. And again, I believe this square is wrong. Okay, and then we substitute this into equation 6, which is already this Euler-Lagrange equation. Okay, and the left-hand side is this. So if we multiply both sides by this square root to the third power, we have something very ugly. I'm just looking if this makes sense. Okay, so what we have on the left-hand side is n prime times the square root to the third power is basically what is under the square root squared again, because it's like 4 square roots multiplied by each other. And here this square root cancels out and 2 square roots remain, which give just this term under the square root without any squares now. So that should be, so those are the first two terms, those before equal sign. And the second part, and we have again this square that shouldn't be here, time, and we have basically the numerator of this. So that's just copied over. Okay. Okay, and I'm just writing that after reduction we get. So basically, what I'm doing here is I'm trying to put all the terms with h two dots. So that's the second derivative of h with respect to x on the left side, and everything else on the right side, and we get such an equation. And I believe that this is correct. I'm trying to see how this square plays into all of that. Huh. I think it might actually be important. Oh no, it's correct. Okay, sorry. I know. I'm silly. Okay. I'm definitely right that this square is actually correct. Why? Because n also depends on x. So when we calculate the derivative of n with respect to x, so you can see how easy it is to make a mistake in such calculations. So if you calculate the derivative of n with respect to x, let me just write it. So the n over the x is the n over the h times the h over the x. So it's n prime times h dot. So this is h dot, this is n prime. So when I calculate the derivative of this, we have n prime times h dot from here, which gives this square, which I said was wrong but isn't. And then if we calculate the derivative of h dot, it just gives h2 dots, and we don't calculate the derivative of n, and we have this second term. So this is correct. Okay, so I didn't actually make a mistake in this document, that's good. But yeah, as you can see, it's easy to miss such a detail. Yeah, anyway, that's the equation we get. If you want, you can check all of this, but you need to know a bit of calculus. But yeah, what gave it away for me is the fact that here we have h dot squared and squared again, which would give a term with h dot to the fourth power. And if this wasn't squared, we would have h dot to the third power here times n prime. So these two wouldn't cancel out. And there is no h dot to the fourth power in the final result, nor h dot to the third power. So these two needed to cancel out, so this square was needed here. And yeah, actually it's correct. Okay, so everything is good in the world again. I see that Truth Nerds makes a bit of fun of what I said. Yeah, I mean, if you know, it doesn't really require a lot of knowledge of calculus, because it's just mechanical calculation of derivatives. You need to know how to calculate a derivative of a composite function like f of g of x. You need to know how to calculate derivatives of products, of ratios, things like that. And if you know that, you can theoretically apply all the rules one after another, and calculate all of this, and you will be able to arrive at the result. But of course, it is true that it's good to have some kind of experience with all of this stuff. So yeah, it's definitely easier if you have experience. If you don't have experience, it will probably look daunting, and yeah, you will probably get stuck. So yeah, but it's doable, and the final result isn't that bad. It could be worse. But what is nice about this final result is this part that's written here. So if we take r to be infinite, this disappears. So we just have 1 in these parentheses, and 1 squared is just 1. This disappears because this has no r in it. And this also disappears because basically this can be written as 1 plus h over r divided by r again. So in the limit it's 0, so this disappears, this disappears, this disappears, and we're left with just this simple equation for a flat Earth. So yeah, it would be really nice if the Earth was flat, because then the equation for refraction would be much simpler, but unfortunately it wasn't to be. Anyway, so those are the two equations I'm actually using in the simulator, and I can show you that just so as not to be not to throw words around. Let me just open what's needed. So this is the source code of the simulator. I'm currently wait. So I'm currently looking at a different part, but oh wait, no, that's the wrong. So that's actually the wrong part, because the Raytracer itself doesn't contain this code. This code is in something, is in a library I called atmospheric refraction. And if we look at this, this is for spherical, those are calculations for the paths on a sphere. And let me look, it should be somewhere here. Oh no, because it's, of course, it's in a different place, because this calc derivative spherical is what we're looking for. And here we have state. So this state is the state of the ray at any given point. It's just the x-coordinate, the h-coordinate, and the dh, which is just derivative of h with respect to x. So that's it. So those three numbers are the ray state. Radius is, it's the radius of the Earth. It's here it's called environment. So the environment, so radius is considered like an outside parameter for this equation. So it's part of the environment, so to speak. Okay, and so the calculation then calculates what is the index of refraction at the altitude h, what is the derivative of the index of refraction at an altitude h. This dn is what I was denoting as n prime. It's just the n over the h, or the derivative of n over with respect to h. And so r, this r lowercase r is h plus radius. So if we go back to, wait, where was I showing it? Okay. So it would correspond to this. So this would be lowercase r in the code, radius plus h. And then we have d to h is just how I denoted the second derivative of h. And this is the first derivative of h times first derivative of h times dn over n. So this is actually okay. So I'm trying to figure out. Okay, so I multiplied the h times radius. Okay, it's a bit harder because what I call the h here. So let's write again. So what I call dh here is actually h dot times r. So this part, no, I hope I remember correctly. So this part is r squared times h dot squared and times n prime over n plus, and this is r plus h squared times again n prime over n plus 2 times h dot squared r squared plus r plus a squared. Okay. So I just wrote it in terms of what was there in the document. So dh here, as I wrote, is h dot times r. So dh squared here is h dot squared r squared times 2. Okay, oh, and it's divided by r. So I forgot about that part. So it's divided by r plus h. Okay. And then here, to get the actual h with 2 dots, I divide what is calculated here by r squared. You can see that I divided by radius twice, so that's capital R squared. So it would be equal here to h dot squared times n prime over n plus r plus h squared over r squared times n prime over n plus 2h dot squared over r plus h, because this r squared gets cancelled, plus r plus h squared over r squared. Okay, so these two terms you might remember from the document. Those are just these two final terms here. Oh, sorry, I can't show you right now for some reason. Okay, yeah. So those are those two final terms here. Oh dear, I just saw that I'm not capturing the cursor, so you can't see when I'm pointing to something with a mouse, which is the problem. Sorry for that. Let me fix this. Okay, you should be seeing my cursor now. Sorry. There were points at which I was pointing to something with a cursor and I had no idea that you weren't seeing that. So those two final terms, which you should be now seeing that I'm pointing to, are the two terms... where was I? Okay, here. Are the final two terms here. And this part is basically just this part that is here. So n prime over n is multiplied by h dot squared, so you can just barely see that we have h dot squared here, and we have it multiplied by r plus h squared over r squared, and it's exactly this fraction. Okay. So we can see that what the code calculates is indeed this same equation, only it calculates it in a bit of a different way, which had some reason. I think initially I coded it differently, and that's basically the reason. Alright, but if we are on a flat earth, it's a bit simpler. So we again take the index of refraction and its derivative, and we have n prime over n times 1 plus dh times dh, which is h dot in this case. So it's a much simpler equation, and that's all. We don't need any divisions by radius, additions of radius, or multiplying by radius. Everything is just as it was. Okay. So yeah. So those are the two equations that the simulator uses, and depending on whether we are simulating a globe Earth or a flat Earth, the different equations are used. And in this document I also put what I called tests, which are basically sanity checks. Yeah, Truth Nerds is saying simpler math is better, flat Earth wins. Yeah, exactly. Yeah, how could I be so wrong? Obviously the Earth is flat because the math for a flat Earth is simpler. That's it. We can pack our bags and close our channels. I guess that is the end. Okay. Anyway, so what I called the tests is basically some sanity checks. So checking if for some known known solutions are actually solutions to those equations. So first check is whether a straight line is actually a solution for when n prime is 0. Because when n prime is 0, it means that the index of refraction of the medium doesn't change with altitude, which means we are in a uniform medium, which means that the paths of light should be straight. So for the spherical case, we get such an equation. And for the flat case, basically everything is zeroed out, and we only get that the second derivative of h is 0. So for the flat case, again, math is much simpler. Second derivative equals 0. It is basically the linear function, which means this is a straight line. And if you don't believe me, well, if we say that h of x is linear, if we take first derivative, then basically first derivative of a linear function is just the coefficient at the variable, and the second derivative, since it doesn't depend on x anymore, is just 0. So this proves that if this is straight, then the second derivative is 0, but this actually works the other way around as well, because if the second derivative is 0, then it means that the first derivative must be constant, because we can just integrate it, and so it's some constant c, and then this means that h, we can integrate it again, and this is c times x plus some another constant d, and again we recover the linear function, which means that this actually describes a straight line. So that is good. Does this describe a straight line? It's a different equation, but also note that this this flat case works in rectilinear coordinates. This equation for the spherical case, since I chose the coordinates in such a weird way, they are not rectilinear, so the equation for a straight line is weirder. It's a bit more complex. So what I'm suggesting here in this document is that the equation of a straight line in polar coordinates can be written like this. So what is this? Basically, it means, okay, let me quickly draw it for you. So let's say we have polar coordinates and we have some point, we have some line. This is the straight line. So if we choose the point that is the closest to origin, this is 0, and if we choose this point, so that this is at a right angle, and let's say this is at an angle phi 0, and it is at a distance r0. So if we take any other point, which is at a distance of r, and at an angle phi, so this angle here, this part, is phi minus phi 0, so it's this inside. It's this term inside the cosine here, and r is just equal r0 over cosine of this angle, which we just said is phi minus phi 0, and we recover this equation. So this works actually for all values of the angle phi. So this is the equation of a straight line. Now if we substitute r equals r plus h and phi equals x over r, we get this equation. So basically because we can get that r plus h equals r plus h0 divided by cosine of x over r minus x0 over r, and that is exactly what is written here, only in an equivalent form. And then if we take this and calculate h dot and calculate h double dot and substitute in this equation, it turns out that actually everything works. So this equation is satisfied. So it works in the spherical case as well. And another check is to see whether this is equivalent to Snell's law, and so that's what I mentioned. So basically Fermat's principle is in a way equivalent to Snell's law. So we can actually check that. So in Snell's law, okay, so the way Snell's law is usually written is that if we have a boundary, and here is n1 and here is n2, and this is, so if we have ray at an angle alpha here and at an angle beta here, the Snell's law basically says that sine alpha over sine of beta is equal to, and so that I don't lie to you, n1 over n2. If we like cross multiply this takes the form that n2 sine alpha equals n1 sine beta. And now we can see that on both sides we have only numbers that relate to the same medium. So we have, for one layer we have numbers on the left side, for the second layer we have on the right side. So we can also write it if there were multiple such layers, and it would like sorry, this probably doesn't work. Anyway, if this was refracted here and here and here, then basically in every layer it would be true that an I times sine of alpha, let's say this is layer number I and it has angle alpha I, so sine of alpha I, this is the same as in all the other layers, so it's constant. So that's why I wrote this Snell's law like this here. And so if we continue from here, okay, yeah, also this is this paragraph, what it says is basically that 1 over h dot equals sine, no, not sine, oh sorry, and I can't do this, so I need to clear this. So 1 of h dot over h dot equals tangent of alpha. So that's basically what this paragraph says, and we can see that this is true because if we are on a flat earth, then basically those layers are all parallel to the x-axis. So if the ray is going at an angle alpha here, the derivative dh over dx is tangent of this beta here, which is cotangent of alpha, because this is simply 90 degrees minus alpha, and cotangent is 1 over tangent. So that means that tangent of alpha is equal to 1 over h dot. Right, so, so if we go further, we have that, yeah, so this is just a trigonometric identity. Sine of alpha is equal to tangent of alpha divided by such a square root. You can check that it's true. It's just true in general, and then we can substitute tangent. Tangent by 1 over h dot. But if we write this as 1 over h dot, it turns out that this 1 over h dot from the numerator combines with the denominator to yield something like this. And then with Snell's law, we would have that the derivative of this multiplied by n, so n times sine of alpha is constant, so the derivative of it is 0. And now we can just calculate the derivative, rearrange the terms, and we get the exact equation that we got for flat Earth from Fermat's principle. Now it might not be immediately obvious, but if we move this nh2 dots to the other side and divide both sides by n, we will get exactly the same equation. Now just a final note is that this equation actually shows, because sometimes people argue, and this is the case that I was talking about in the beginning, so sometimes people argue that Snell's law says that if we have a boundary, and we have like n1 here and n2 here, and the light ray travels precisely across the boundary, so what then? So the angle of incidence is 90 degrees, but why should this light ray actually go either way, or should it not, or should it just travel along the boundary? And Snell's law doesn't really answer that, because you can't really have a 90-degree angle here without this light ray already traveling along the boundary for some time, right? Because well, what do you have this angle to then? Although, yeah, well, if this is an infinitely thin layer, then you could say that this ray was like curved and it entered like tangentially. Okay, but what then? What does Snell's law say about it? And it doesn't really say much. But with Fermat's principle, we can just calculate the path, like considering everything as a whole. And it turns out that if there is some gradient of the index of refraction, so this is non-zero, then the second derivative of h is also non-zero, which means that the ray will be curved and it won't be able to just travel along a straight line. Oh, truth nerd is nitpicking, but yeah, okay, good point. Sine alpha equal to tangent alpha over square root of 1 plus tangent alpha is true for acute angles, but not all angles. Yeah, so yeah, you're right. That will probably not work for all angles. Yeah, because square root by square root by definition is the positive part, and sometimes it would have to be the negative root in order for this to hold, I think. I'm not sure, but I think. But anyway, yeah. Oh yeah, wrong sign for e.g. 5 pi over 4, yeah, so that's probably the problem. Yeah. Okay, good point, thanks for the correction. Okay, anyway, my point here was that, yeah, with this equation it's clear that, so So yeah, some people try to argue from Snell's law that over a flat Earth, horizontal rays should travel horizontally all the way because, well, they can just travel along the boundary between the layers. But Fermat's principle makes it clear that it isn't so, and if there is a non-zero gradient of the index of refraction, then even a horizontal ray will be curved, and it will actually be curving the way the gradient is pointing, so towards the growing index of refraction, which means that if in a typical atmosphere index of refraction grows down, and it does because density grows down, density is larger towards the lower parts of the atmosphere, then this will be negative, which means H double dot will be negative, which means the ray will be curving down. So we have the refraction that's bending light down in the typical gradient. Okay, so that at least should complete the part about refraction I had for you. And we are already over an hour into the stream, and that's just the first out of 6 parts, so I don't know if I'll be able to finish today. So let's just quickly go through the Earth shape model, because the really one of the really interesting parts is the atmospheric model. So, okay, let's just go into the Earth shape. What I wanted to tell you. So yeah, so one thing I already told you, that that the Earth shape model is what decides which of the equations is being used, and I actually showed you that in the code. So we have those two derivatives here, and here we have like code for paths on a spherical Earth, and you have this code to calc derivative spherical, and separately there is for flat Earth. So I will just quickly show you that this one calls calc derivative flat here. And now I think we need to, no, wait. So I'm trying, okay. So I'm trying to remember where in, okay, so there is this function called cast ray, which you supply which, depending on the shape that is assumed, which is either flat or spherical, chooses whether to use the spherical version of line or the flat version. So yeah, so that's basically the code that's responsible for it. Okay, but the other part is okay. So now I must go a bit into the details of how the simulator actually traces rays. So whenever when the simulator generates an image, it chooses a pixel. The pixel has some coordinates. It does some math, which I intended to go through later to translate it into a direction in 3-dimensional space. And then this direction is then split into 2 angles, the azimuth and the elevation angle. So basically elevation angle is the angle to the horizontal plane. Right, we have some horizontal plane, and this makes some angle with that plane, so that's the elevation angle. And the other angle is azimuth, so let's say somewhere here is north, then this angle is the azimuth of this ray. Now, what is important is in such a simulation where nothing changes horizontally, so the index of refraction only changes vertically, the only thing that is important for the path of the ray is this elevation angle. The azimuth plays no part in it, everything is symmetrical around the vertical axis. So basically whenever it casts a ray, it only uses the elevation angle to do that. Now, then what it does is it calculates a path. So it starts at x equals 0, and it has some h0 here. And the elevation angle determines the initial derivative, so we have this elevation angle alpha, and then tangent of alpha is basically the initial derivative of h. So those are the initial conditions, and then the program uses the Runge-Kutta integrator of the fourth order. I mentioned it already in the Coriolis live stream, I think. I won't go into the details here because it would make this stream even longer. Anyway, it's a method of basically going step by step and having some initial conditions and the differential equation, which we do have because I just showed you this equation for h2 dots equals like n prime over n, 1 plus stuff, etc. Right, so we have this differential equation. We can calculate h2 dots from h dot, h, and x. And then we can basically step by step propagate, so we can calculate the next, like h1 and h2, and h dot 1, h dot 2, etc, etc. And so we have some kind of a path, right? So there is x1, this is at x2, and then there is another at x3, etc, etc. So we have just this sequence of points that represents the ray, but note that this x is just the distance along the surface from the starting point. Nowhere here do we have the precise coordinates of where the ray is on Earth, but knowing the initial coordinates, so knowing the latitude and longitude of the starting point, so we have latitude, we have, sorry, let me write it like this, knowing the latitude and longitude, and knowing the azimuth, so the azimuth also enters here, and knowing the distance, so basically knowing this x, we can calculate what is the latitude and longitude of the final point. So for example, if we know that the ray intersected the terrain at x equals, I don't know, 100 kilometers, then knowing the starting point, knowing which azimuth we were tracing the ray in, which wasn't important for the tracing part itself, it wasn't important at all, because at any azimuth the path would look the same, but now when we want to calculate the final position, we need to translate this azimuth and distance, which is 100 kilometers, into latitude and longitude of the intersection point. Also, for even testing whether it intersects the terrain, we need to do this, because the terrain elevation can be different in different directions, right? So we need to know if at x equal 100 kilometers the terrain is at this elevation or at this elevation, and to do that we need to use the azimuth, the distance, and then calculate that into proper coordinates. And the way this is converted into the coordinates of the final point depends on the Earth model. And initially, again, this was the same thing as the model that decided the equation. So there were only two options. There was the option of spherical and there was the option of flat. So in the option of spherical, the way it is being done, and I don't know if I have time to go into details, I intended to, but okay, let me do this quickly. So we have the starting point, right, which is some latitude and longitude, and this is usually denoted by phi and lambda, which is confusing as hell to me, because I'm used to phi being the angle that is analogous to longitude, but in geography usually longitude is denoted by lambda and phi denotes the latitude. So let's just keep this convention here for now. So if this is the equatorial plane, then this is the latitude, and if this is 0 degree longitude, this is the longitude, right? Okay, yeah, I drew this like shit, but anyway. So we can associate a vector that is pointing from the center to this point with those coordinates, and it's actually fairly simple, because this vector, if we imagine that the x-axis is here, z is polar axis, and the y-axis is just perpendicular to x, so that this forms a right-handed coordinate system, then we have that this vector is just cosine of 3 cosine of lambda cosine of phi, sine of lambda, and sine of phi. So that's the vector. So that is the vector to this point. Now, we also want the vector pointing in the azimuth into which we were moving. So for that, we will need a vector that points north, and we will need a vector that points east. And so this, let's denote v. There will be a vector that points east, and it's actually quite simple because vector pointing east will always be perpendicular to z, so it will have 0 z coordinate. And now, so I don't lie to you, I believe it will be cos lambda, and here it will be minus sine of lambda, something like that. So that will be the vector pointing east. And the vector pointing north will be a bit more complex, so it will have cosine of phi here, and then it was minus sine of phi cosine of lambda and minus sine of lambda. Okay, like this. Okay, and these should be orthogonal to each other, and yeah, I quick checks and lambda cos lambda. Okay, and they are okay. Perfect. So we have vector that points north, vector that points east. Then we can, from this and the azimuth, so let's denote the azimuth by alpha. So from this we can figure out the vector of direction into which, so the vector of direction will be a vector horizontal, so tangent to the Earth's surface, in the direction in which the ray started initially, right? So this will just be Vn times cosine of alpha plus Ve times sine of alpha. Is that simple? So when we already have those two vectors, one pointing north, one pointing east, it's very easy to calculate this vector in the starting direction. Yeah, Truth Nerds is writing that the scalar product of every pair of these three vectors is 0. So the dot product is 0 when the vectors are perpendicular, and you calculate the dot product by multiplying the first coordinate by the first coordinate, second by the second, third by the third, and adding all of these together. So if we do that for the first two vectors, for example, we will have minus sine lambda cos phi plus sine lambda cos phi plus 0, so this is 0 in total. And the same goes for every two pairs, for every pair of two vectors out of these three, so they are all orthogonal. Okay, so when we have this direction, now, okay, and now my drawing skills will be really put to the test, and they are not very good. So this direction, this is, let's say, VD. So in this drawing, the ray started somewhere to the northeast, right? So what we're really interested in is the great circle that passes through this point, and it passes through this point in this northeastern direction. So we are interested in such a great circle. But to get this great circle, what we can do is we can take a vector that is perpendicular to the plane of this circle, which fortunately can be easily calculated by just taking this V and calculating cross product with VD. So this is V cross VD. And then rotating the initial V by an angle proportional to the distance that we're looking at. So we'll take angle beta, which will be just the x, which is the distance along the great circle divided by radius of the Earth. And then we will just rotate this V around this axis of V cross VD by the angle beta. And we will get the final position. So that's basically the way this is calculated on a spherical Earth. So that's the spherical Earth model. And on a flat Earth model, it's actually easier, again, easier math, so Earth is flat, definitely. So on flat Earth, we take, and here is the okay, it's not, there is a slight issue here, but, so, for example, let's take the azimuthal equidistant flat Earth model, in which the North Pole is in the center. So on such a model, basically the latitude corresponds to the distance from the North Pole, and to be precise, the distance from the North Pole is actually it's actually not latitude, but 90 degrees minus latitude times some constant, and this constant is this 111 kilometers per degree, or 69 miles per degree, or what have you. So this will be equal r, and longitude is actually easy because we still have the 0 degree meridian, and we just have this angle, which is the longitude. And so if we have two such points, then we just have 2 points on a plane. From this we can calculate r, and we have lambda 1. Oh, sorry, this was supposed to say 1. And from this we have r2 lambda 2. And from this we can calculate x2 equals, okay, can you still see it? I'll just turn off the camera for now. For this we have x2 equals r2 times cosine of lambda 2, y2 equals r2 times sine lambda 2, and the same here, x1 equals r1 cos lambda 1, y1 equals r1 sine lambda 1, and we have just xy coordinates, and so we can calculate the distance by square root of x1 minus x2 squared plus y1 minus y2 squared. So that's how we can calculate the distance. And if we have the reverse problem, so we have some direction which is at azimuth alpha, again we need to calculate the vector that is pointing north, the vector that is pointing east. So vector north in this case will be, so let's say we are at this point x1, y1, so vector north will be simply minus x1 minus y1, and vector pointing east will be this, only rotated to 90 degrees to the east. So if this is x, it needs to be, so, oh Jesus. So let me think for a moment. This would be positive x, positive y, and we need positive y, negative x. So it will be negative y1 and x1, something like that. If I didn't make a mistake, so that would be the vector to the east. Again, we can calculate the direction vector, this initial direction, in exactly the same way. So north vector times cosine alpha plus east vector times sine of alpha, and then we can just take x1, y1 plus vd times x, which x is the distance in this case, and so we land here, and from x2 and y2 we can recover r2 and lambda 2 very easily. So r2 is just square root of x2 squared plus y2 squared, and lambda 2 is equal to r cosine of y2 divided by x2. And to avoid problems in software, usually what is used is 2-argument arctangent, which is called a tan 2 usually. This is what I actually used in the code. So then I don't need to care about signs or whether x is 0 or not. The function takes care of it for me. And when we have r and lambda, r can be converted to the latitude again, and we have a latitude and longitude of the final point. So that is the math of the flat plane in the azimuthal equidistant model. But, and here is something I will show you, this causes some trouble, Because okay, okay, let me show you. So this is a simulation of a view in New Zealand. It's basically looking from the northern island of New Zealand towards the southern island of New Zealand in some kind of a bay. There was a video with this view somewhere that was titled 1000% flat Earth proof, as is usual for such videos. So this is actually a simulation of this view on the globe Earth. And what happens if we take the same setting? So you can see heading toward this mountain is 232 degrees, and the mountain is quite big. So what if we use exactly the same setting, so the same azimuth, the same field of view, and simulate it on an azimuthal equidistant model? So let me show you. I won't show you different ones. So this happens. We see nothing. And that is not a mistake of the program. That is the problem of how much azimuthal equidistant model distorts stuff on the southern hemisphere. It turns out that the distances get distorted and the azimuths get distorted. So actually the mountain is on a completely different heading, on a heading of roughly 257, and it is much smaller because it is much more distant on this map. So you can see that it looks like this, and on the azimuthal equidistant it looks like this because it is much farther, so it is smaller due to perspective. So that is kind of a problem for the azimuthal equidistant model. So in order to give flat Earth any chance at all, I invented something that I called the flat model back then, because this was basically when I simulated this New Zealand and got nothing at all. I decided, okay, that's not something I can show in a video, for example. So I decided to create something that would give any chance at all to flat Earth. So yeah, so what I created, I'm now calling distorted flat model, or flat distorted, something like that. And the way it works is basically, okay, it's a bit crazy, and it really makes no sense. It's internally inconsistent, but at least it gave some views on a flat Earth that looked like something and not just nothing, because we are looking in a completely wrong direction. So the way it works is, I assume that latitude and longitude actually form a rectilinear grid. So if I'm at point phi lambda, so I assume that the phi axis is here, the lambda axis is here, and then what I'm doing in that model is, so I'm scaling the phi axis times this constant of 111 kilometers per degree, and lambda I'm scaling times this constant, but times what was the cosine of phi? Okay, and then I'm basically just taking a vector that is at an angle alpha to this north-south axis, and then go in such coordinate system by a distance of x, and then calculate what would be the phi to lambda 2. I won't go into detail because it's... So the big problem with this model is that, for example, if it's not consistent, because if I start from a different point, for example, probably if I started from a different point on this line here and started in a compatible azimuth, I wouldn't even land in the same point, because now I would use a different scaling for the x-axis and I would land in some completely different space. But at least it scaled the immediate surroundings in such a way that it gave results that looked like, well, that looked reasonably. So if I'll show you... Right, so this is the AE and this is the distorted model. So as you can see, the mountain is now again visible at roughly 232, well, if we go back, the peak here was more like 231.6, and if we go to the flat distorted model, it's at 232 point, I don't know, 0.1, let's say. So the headings are still a bit distorted, but that's actually okay, because we don't really, well, in the AE model they are completely distorted, completely different, and nobody really pays attention to that. So I wasn't really concerned by this, and it also shows that much more of the mountain is it may be not that clear when I'm just jumping through multiple different images in the meantime, but if you put those images side by side, it's quite clear that on a flat Earth the mountain would be basically much higher, because nothing would be hidden behind the horizon. So that was the model for the flat Earth that the simulator used for a long time. That was the only flat model available, this distorted one. But quite recently, oh hello Sable Eagle, you can centrally or azimuthal equidistant map projection within North Island and get a pretty good map of North Island. Yeah, exactly. So that's what I did actually in a newer version. So basically when the old version had only spherical and flat, now you can choose between spherical, flat distorted, which is the old flat, so which is this. You can choose azimuthal equidistant, which is what I showed you here, right? Which is azimuthal equidistant centered on the North Pole. And the fourth option is azimuthal equidistant centered on the observer. And it looks like this, and if we compare, then the headings are still the same, as you can see, so the peak is in exactly the same direction as on a spherical model, only more of the island is visible. But as you may be able to see, okay, I think you see a part of it. Oh, let me put the camera on again. So this I called flat spherical, and this is probably something that would like induce confusion in many people, and I understand that. I just didn't. Well, I could have called it azimuthal, like observer centered AE or something like that, because essentially what this is, it is an observer centered azimuthal equidistant projection. But why I called it flat spherical? Because in a sense it's a mix of the flat model and spherical model. It's the spherical model of distances, it's the spherical model of basically translating coordinates, translating distances and directions into coordinates, what I showed you here in this. So basically when I'm doing this flat spherical model, I'm doing the same calculation as on the spherical model when translating distance and azimuth into target coordinates. But at the same time it uses the flat equation for refraction, so it uses this differential equation from the flat model, in which sense it makes it a mix of the flat and spherical models, and that's why I called it flat spherical, but it might be confusing, so I'll probably rename it at some point. I just didn't get to that yet. Oh, I see we have pseudo-idealand. I know he's a Polish guy, so this is actually pronounced pseudo-idealand, not pseudo-idealand, I think. At least that's how he was pronouncing it on his streams, so hello. Right. So yeah, so that's what I want to say about the shape models. So now there are 4 available shapes, and this is how they work. Right. And actually, I think this flat spherical or observer-centered azimuthal equidistant is mostly what people would use in comparing flat Earth to spherical Earth, because the only thing it changes is how much things stick up from beyond the horizon, or basically how much things stick up, right? Because you see exactly the same things in exactly the same direction, only there is more or less of it visible. So that's usually what we are interested in when we are comparing flat to spherical. But if you really want to highlight the differences between a globe and azimuthal equidistant, you can use azimuthal equidistant, and you can show that in azimuthal equidistant you get this. And actually, thanks to this, the azimuthal equidistant model can even be falsified using a compass, because if you are on the northern island of New Zealand and you are looking towards the mountains of on the southern island, and the compass tells you that you are looking in the direction of 232, well, you would need to take into account the magnetic declination, and I can already hear Brian's logic saying that magnetic declination is invented so that this fits the globe model. But yeah, if you include the magnetic declination, you will notice that you see the mountain in the direction of 232, but on a flat Earth in the direction of 232, you should be just seeing the ocean, and the mountain should be visible in a completely different direction. So even that could be used to debunk the flat Earth if someone subscribes to the azimuthal equidistant model. And of course then if they have a theodolite, they could measure the angular size, and it would turn out that the mountain is much too big to be explained on the azimuthal equidistant model, because it's much closer than the azimuthal equidistant model would predict. So yeah. Okay. So that's this covered. So let's go to the third part, which is atmospheric model. And this part will be longer, and we are already almost 2 hours in, which is not good. Okay, so what I want to show you regarding the atmospheric model. So what the atmospheric model does, really, it's a way of defining how pressure and temperature depend on altitude, and then this is recalculated by the program itself into the refractive index. So that's how you define refraction, really, in the simulator. So I already mentioned that in the first part, in the general overview part of the simulator, but let me just reiterate that here refraction is not defined by the coefficient of refraction, so you won't find 7/6R or any other effective radius anywhere in the simulator. The way refraction works here is you define the atmosphere. I can even show you an example. Wait. Okay, let me maybe do this. Okay. Okay, I will show you later what this all is about, but basically atmosphere is defined by defining pressure at some altitude and then defining temperature. This is probably cryptic for now, but I will explain in a moment what all this means and what happens here. Right. Anyway, the way you define atmosphere is basically what I showed you. So you define pressure at some altitude. So let's call this altitude H0, and you define it to be some value P0. So you supply this and you supply this, and then you also define T of H, so temperature as a function of altitude, and this can be defined in a few different ways. So initially, well, completely initially in the very first version in the refraction calculator, you wouldn't even define anything because it just used the exponential, basically the exponential, how do I put it? Well, exponential decrease of the part of the index of refraction that was after 1, right after the comma. So it was 1 plus something that was decaying exponentially with altitude. In the subsequent versions, you could already define some atmosphere, and you would define this pressure at some altitude, and you would define temperature by defining again temperature at some height. Let's call it height 1 because it could be different than this one. Do I remember correctly? Yeah, I think so. So you would define temperature at some altitude 1, and it would be defined to be T1, and then you could define gradients. So basically, the way it would look, what it would look like was if this is altitude and if this is temperature, you would start at some point and then you would define gradient. So we would, for example, define that temperature was growing with altitude at this point, so it would define temperature to be this. And then you would define that at some altitude this gradient switches to some different gradient, and at some altitude it switches to yet different gradient, and at some to different. So you could compose the dependence of temperature on altitude from such linear functions. So it would be like a piecewise linear function, right? You could compose it from such linear pieces, and then you could get pretty much arbitrary shape, but of course it would have these points where the temperature would where the gradient would abruptly change. Fortunately, that's not a problem, because if you calculate the derivative over the h, if I remember correctly, for some reason the derivative of temperature wasn't really coming into play here, or at least the density was continuous. I don't remember. Anyway, it was possible to calculate this derivative of derivative of index of refraction, even though the derivative of oh no, okay. Actually, the derivative of temperature was coming into play, but it wasn't a problem, because what would be a problem would be if there was a second derivative of temperature, because that's undefined at this point. Technically, the first derivative is also undefined, because if we look at t prime, it would look something like this. So it's this value, and then it's this value, and at this point it's undefined whether it's this or this. But since this is just a single point, that wasn't a problem. The problem would be if we needed another derivative, and then this would break down, because it would be infinite at this point. But fortunately, the highest derivative needed for this was the first derivative, and this could still work. So, but to calculate the index of refraction at a given height, basically what the program would do would be calculate temperature at this height, which is easy because we just take it directly from the definition. Knowing this point and all the derivatives here is completely enough to calculate a temperature at any given height. Basically, you need to check let's say we are interested in the temperature at this height, so we need to check into which interval this falls into, and from the temperature here and the gradient here, we can calculate the temperature at this height of the switch over to a different gradient. Then we can use this gradient to calculate the temperature here, and then we can use this gradient to go from here to here. So we can easily calculate the temperature at any given height, but we also need the pressure at this given height. And this was a bit more complicated. So the way this works is we need to solve a differential equation, of course, because how else would we write a simple program, right? We need more differential equations. So the way this works is it uses two things. First, we use the ideal gas law, which you might know. It's pressure times volume equals number of moles times the gas constant times the temperature. So actually, in order to use it for the simulator, I needed it in a slightly different form. So let's reformulate it. We move v to the right side, and we get this. And n, which is the number of moles, we can take to be the mass of gas divided by the molar mass, so the mass of a single mole of gas. So we will write that P equals m over mu v RT. And this mass divided by volume is just density. So we have that this is equal to density RT divided by molar mass. And that's the equation. It's equivalent to this ideal gas equation, this well-known one, but it's a bit nicer because it ties pressure, density, temperature, all of which are local values. So they are valid at a single point in the gas. Well, technically not quite if we look microscopically, but if we view the gas as a continuous medium, medium, all of those values are valid at a single point. Whereas where we have volume or the number of moles, this needs some some volume, some non-zero volume of gas. So that's harder to use, but those, well, so nicely it is said that volume and number of moles are it was called extrinsic, I believe so. Okay, I might be confusing something. I don't know if it's called that in English, but at least in Polish it sounds something like extrinsic values and intrinsic no, sorry, extensive and intensive. Oh, yeah, those are the words. So volume and number of moles are extensive values, which means if you have two systems, one system with one volume and second system with second volume, if you connect them into one system, the connected system has the volume that is sum of those two, right? The same goes for number of moles. If you have N1 and N2, if you connect the two, you have N1 plus N2 moles. Whereas pressure, temperature, and density, they don't add. If you have one system with pressure P and the other with pressure P and you connect them, the total system still has pressure P. It doesn't add. So that's what it means for a value to be intensive. You could of course ask what happens if there is a pressure P1 and P2 and what happens when you connect them, but the answer is, well, it's not an equilibrium. Something will happen then. All right. So this equation, this form of the equation, P equal rho RT divided by mu, it has no extensive values, so that's nice. And R and mu are constant, so that's also cool. And the second equation is actually called the hydrostatic equilibrium equation, and you might be wondering why hydrostatic equilibrium when we're applying it to air. But I think that, well, usually things that have hydro in their name refer to water, but I think in this case it's more from fluid than water, and both gases and liquids are considered fluids in physics because they have many of the same properties. And hydrostatic equilibrium is that the derivative of pressure with respect to altitude is minus the density times g. G as in gravitational acceleration. So if we combine the two, we get that the derivative of pressure is equal to minus mu g divided by RT times P. And this is an ordinary differential equation. Let me take a sip of water. Okay. So this is an ordinary differential equation which can be solved if we know how t depends on altitude. Well, in some cases. But in the case of t depending on the altitude in linear fashion, it's quite easy. So if we say that t is some constant a times h plus some t0, then we have that dp over dh equals minus mu g divided by r, and we have a h plus t0 times p. So we can shuffle this around, we can move p to the left side, dh to the right side, and we have dp over p equals minus mu g divided by r ah plus t0 dh. And this can be integrated. So we have log p equals, and this is minus g divided by r by ra log ah plus t0 plus some constant c. So that's the solution to this differential equation, and then we can raise e to the power of both sides, and what we get is that p equals e to the power of c times AH plus T0 to the power of minus G divided by RA. So it is such a power law. Now if we extract T0 from here, what we will get something like this, that it is at e to the c times T0 to the power of minus G divided by RA. So this might seem a bit weird at first, because this might be a very weird fraction, and what does it mean for the temperature to be raised to such a fraction, but in a moment it will make sense. And then we will have 1 plus A divided by T0 times H to the power of minus G by RA. And now, if H is equal 0, then this whole thing is equal 1, and basically we get that P of 0 is equal to just this part, e to the c times T minus G divided by RA. So we can just erase this and write P0. Tada! And we have such a law for the pressure. So if temperature changes in a linear fashion, then pressure changes with such a power law, which is nice. We have a nice solution. So then if we know the pressure at a single altitude, and we know the gradient of temperature, which is this A here, which is here and here, if we know this gradient of temperature, and we know the temperature itself, we know this T0, which is temperature at an altitude of 0, we can calculate how the pressure is changing in this interval where temperature behaves linearly. So then basically if we have, let me turn off the camera again because it's eating up precious real estate on the screen. So if we have some interval of altitudes here, where temperature behaves in a linear fashion, and we know pressure somewhere in this interval, so if we know pressure for this altitude, for example, we can calculate from this equation pressure both at this end and at this end and along this whole interval. And if we know pressure at this end and at this end, if we know the gradient at a different interval, then we know the pressure at one point of this interval, namely this edge of the interval. And we can calculate the pressure at this whole interval as well. So using this equation and and our knowledge of temperature in the atmosphere, we can calculate the pressure everywhere as well. And then using that, we can calculate the index of refraction. Although one note: what happens if A is 0? If A is 0, it means that temperature is constant, which means that if this is altitude and this is temperature, it means that this is vertical. So what happens if A is 0? This becomes minus infinity, and we have 1 to the minus infinity, which is what the fuck. Okay, no, that doesn't work. So we need to go back here. We need to go back to this equation, and we need to solve it with A equals 0. So we have then dp over p equals minus mu g over rt0 dh. So T0 is a constant, so now everything here is a constant, and we have that log P equals minus mu GH divided by RT0 plus a constant. And now again e to the power of both sides, and we have P equals e to the c times e to the power of minus mu GH divided by RT0, and again substituting h equals 0, we have this is equal to 1, and this will become, and we will see that P0 is equal e to the power of c, so we can erase that and we can just write P0, and we get the exponential change in pressure. And this thing is what is called the barometric formula, and it is sometimes used as an approximation for how pressure changes with altitude. If you ever hear someone saying that pressure changes exponentially with altitude, they mean this formula, which is valid when temperature is constant. The temperature unfortunately isn't really constant in the atmosphere, so it's more complicated than that, but this is still a good approximation. Okay. Right, so that is what the state was at some point. Oh, one more thing, I will just let's get this out of the way. So when we have P of h and we have T of h, we have pressure and temperature, how do we get the refractive index? So there is such a thing. Let me show you. There is a nice website which shows two equations that can be used to do that. One is called the modified Edlen equation, and one is called Sidor equation. So there are two equations, and I actually chose the modified Edlen equation for my simulator. I think Sidor equation is newer and more accurate, but if you look at this table here, you can see that the differences are pretty much negligible between Edlen and Sidor. So it really doesn't matter much which one is chosen. So I chose modified Edlen because it seemed simpler. I don't think it's actually that much simpler, but still, that's what I have right now, and that's what I'm using. If we look at, let me see. So if we look at how to actually calculate this. Okay, there is the Sidor calculation, so you see there are a lot of constants, and then you calculate a lot of factors, etc., etc. So if you're wondering where such equations come from, those are simply best fits to empirical measurements, as far as I know. I mean, there is some theory behind it, so the general form of the equation comes from theory, but then the coefficients in this equation are just best fits to empirical data. So the people basically take air in the lab, they put it in some container, they control the pressure and temperature and humidity, and then they simply measure the index of refraction. They take a note, and then they calculate it for many different sets of conditions, and then they fit some equation that fits all the data that they collected, and that's basically how this happens. So that's why those equations are so weird, because they are basically just fits. It's not something that comes out of some general law that it has to be this form. It's just an approximation that is a best fit to known data. And here is the Edlen calculation. So if you compare this, there is a lot of constants here. There is a bit less, a bit smaller number of constants here, so that might have been what made me decide on this equation. It's actually fairly simple. You calculate this, substitute it into the next thing, and basically you have this whole index of refraction. One thing to note is that actually this whole both these equations can take humidity into account. So this, it says calculate partial pressure PV, so this partial pressure is the partial pressure of water vapor in the air, and you calculate it using relative humidity and temperature, I believe, and that should be all, because I think this doesn't really depend on pressure. Oh no, actually there is some dependency on pressure apparently here. Anyway, it can be calculated. So this way it is possible to actually include humidity in the calculations as well. I haven't done this so far, so my simulator just assumes humidity to be 0 everywhere. Fortunately, the influence of humidity isn't that big. The change, I calculated it for someone under my video recently, and the change at 15 degrees Celsius from 0 humidity to 100% humidity, so from completely dry to completely moist air, changes the index of refraction the same way as changing the temperature by 0.6 degrees. So it's not a huge change, and it can also be like simulated by changing the temperature. You will get the same index of refraction by just changing the temperature by a fraction of a degree. So I never considered this a very important part of the simulator, but there are people that raise it as a counter argument that I just assume the humidity to be 0 and it's incorrect. So I'll probably code this in at some point so that humidity will also be possible to define the vertical profile of humidity, but I don't know if it will get much use. Anyway, yeah, that's basically what I'm using to calculate all this stuff. And again, if you want to see the code, this is all here. So actually, I already have the code for calculating the water vapor pressure. It's pretty much unreadable because it's directly copied from the website, so it only makes sense in the context of the website if you look at it. And the calculation of refractive index, as you can see, it uses the modified Edlan equation. So those are just coefficients that are directly copied from here, those A, B, C, D, E, F, G. So these coefficients are just here. And then this is just this whole calculation that is described on the website combined into a single function. And this calculates the derivative of the index of refraction, and it takes a bit more arguments because it takes the pressure, temperature, relative humidity, but it also takes the derivative of pressure, derivative of temperature, and derivative of relative humidity. So you need to calculate that before you input it in here. And yeah, basically the simulator, if I remember correctly, it's the simulator that is doing that, or no? No, I think it's here. If you look at the pressure, there is a bit of scary maths here as well. No, it will be here. Okay, yeah. So you can see that you can take this atmosphere object and you can calculate the derivative of temperature, and you can calculate the derivative of pressure, and derivative of pressure is simply calculated using this equation, using basically this. So only instead of this, it's the H here and it's P here. So it takes the pressure, it takes the temperature, and it does this calculation to calculate the derivative of pressure. There is a good reason for doing that, and the reason for doing that is the more complex expressions for pressure when the temperature is not a linear function, because in a recent version of the simulator I also introduced a way of defining temperature using cubic splines. Cubic splines are basically a way of interpolating between points. Let me just Google this because there was a good article on Wikipedia, if I remember correctly. Right. So this actually shows an algorithm for calculation. Anyway, wait, I have a better link somewhere. So this is, I think this is nicer. Okay, oh, right, yeah, for example, like this. So you have defined points, and then from these points you can do an interpolation. So every piece, those lines are actually separate functions. Every line between two subsequent points is a separate function. All of them are cubic functions, which means they have like terms with x cubed, x squared, x, and a constant term. So those are cubic polynomials, and they are chosen in such a way that the derivative is continuous, which means that basically you won't get a sharp edge anywhere, because the derivative of one side, which means the slope of one side, is the same as the slope of the other side, and they connect smoothly. Well, smoothly in the mathematical sense would mean that all of the derivatives, infinitely many derivatives, are the same, so it's not this case. But to a human eye, it appears as if they connected smoothly because there is no like cusp or anything, right? So that's why cubic splines are nice, because then you just set a few different points and the computer can just calculate the best fit as a curve that is composed of those cubic polynomials, and it passes nicely through the different points. And this is actually doable in the current version of the simulator, so I can just show you. I prepared, so that's actually what you could see in, wait, where was this? Oh, here. So here, wait, not this, this. So here you have an atmosphere defined as a piecewise linear function. So this basically says that we have a fixed temperature at 0 altitude defined to 277 Kelvin. Temperatures are specified in Kelvin. It's probably not the best UX, but that's how I did it. And pressure at altitude 0, is defined to be basically 1 atmosphere. It's in hectopascals. So then first temperature function means it's the function that is that applies from the altitudes of -infinity to basically whatever is the next function. So here the next function will be at altitude of 0.5 meters. So this first function would apply to the interval from -infinity to half a meter. Oh, hello, Clive Wells. Nice to see you. Right. So in this case, it's just a linear function with a gradient of -6, and -6 means -6 Kelvin per meter, which is a huge gradient. But since it's relevant only, well, theoretically from -infinity, but unless we have a depression somewhere, then from 0 to just half a meter. So it's like 3 degrees difference, which can happen if the surface is warm for some reason. And from half a meter onward, the gradient is -2 Kelvin per meter, which means that on the space of another meter, the temperature drops by 2 Kelvin. Then from 1.5 meter onwards, it's plus 0.66, so the temperature starts growing instead of falling. Then at 3.25 meters, it switches to -0.2. At 4 meters, it switches to -0.0065. Which is the standard gradient defined in the US 76 atmosphere. So basically, and from 4 meters onward, it's this standard gradient. So I basically defined a layer of 4 meters of air that has some weird things happening to the gradient of temperature, and then from 4 meters onward, it's a standard atmosphere. So that's if you use only the linear functions, and that's something that only the linear functions were available up to a point, but now it's also possible to do it with splines. And defining stuff with splines works in a bit of a different way. So we define a set of points. So here I define that I want the temperature at 0 altitude to be 277, at half a meter altitude to be 274, at 3 meters altitude to be this, and at 4 meters altitude to be this. And I also define boundary conditions, because it's not enough to specify just the points, because that still leaves some degrees of freedom for the splines. So you also need to set some conditions on the edge points, so on the first and on the last point. And this is doable in a few different ways. One possibility is to set the derivative at these points to be some constant. So then basically you define what the initial and the final slope should be, and that already defines uniquely all the splines in between. Or you can, for example, say that the second derivatives should exist and be 0, which then means basically that it should smoothly pass into a straight line. But it might have a different derivative than here, because if you force the derivative to be some value, it is possible that actually actually the second derivative will it will be 0 from one side, yeah, but from the other side it might be non-zero, which means that the second derivative might not be continuous. If the other boundary condition is for the second derivative to be continuous. So it means that the second derivative should be 0 at the ends, and then it can smoothly pass into a straight line. And yeah, I think that was it. There might have been a third way of defining a boundary condition, but I would have to, let me just check. Because I also wrote the utility, the library for cubic splines for this particular application. And it should be defined, yeah, derivatives. Okay, yeah, so you can define what the second derivatives should be at every end. And there is the natural condition, which means that second derivatives at initial, what is written here, at initial and final points are set to 0. So basically you can set second derivatives to 0 explicitly using this condition, or you can set it, or you can say it should be natural, which means naturally they should be 0. It's the same. But with these second derivatives you can also specify some different second derivatives. And there is also a way you can say periodic boundary conditions, which basically means that one end should, if you made a loop out of it and connected the two ends, they should also connect smoothly. I don't even know if this works. I think that it's possible that for periodic, oh yeah, exactly. If you look at here, periodic says unimplemented, so if somebody even tries to use this periodic condition, it will throw an error. But the other variants work. And this basically, the algorithm for calculating those splines is described on the wiki, so I believe that it was just described here, algorithm to find the interpolating cubic spline. So I think I just used what was described here and I didn't think too much of it. Wait, that's regular Wikipedia, I think, oh yeah. It's described here, methods, yeah. So TruthNerd says implementing periodic is left as an exercise to the user, precisely. Yeah. So yeah, I just used the method that was described here. It's a lot of equations, but once you read into them, it actually makes a lot of sense and it's not that complicated, but I won't really go into the detail right now. If you want, you can see this link here. I can post it in the description as well. I might forget, so if I don't post it and somebody is interested in this link, please let me know. I will just paste it into the description and probably in the comment and in a response to your comment if you write something like that. Alright, but the main problem with those cubic splines is that now so what I've shown you here was a solution to the equation for pressure when temperature depended on altitude in a linear fashion. And now the dependence can be cubic. So that complicates stuff quite a bit. So now we have something like this. So we have dp over dh equals minus g over r. And now we have T0 plus AH plus BH squared plus CH cubed times P. And this equation is quite a bit harder to solve. I mean, the first step is still the same, so we just exchange those two. We have dP over P here, and we have dH here. And we need to integrate this stuff. So there is actually a method for integrating such functions. It is integrable analytically. Only you need to know the roots of this polynomial. And solving a cubic polynomial is not such a straightforward task. I mean, well, it's not that much harder than cubic polynomials, but it is not usually taught at school, so it's seen as a bit of more magic. But basically, this polynomial, we need first to change this polynomial into CH minus H1, H minus H2, H minus H3, or, because this might be impossible, it might turn out that actually that two of the roots are complex and not real. So the second possibility is H minus H1, H squared plus, I don't know, some D1H plus D2. So we need to change this into one of these forms. And then when we have that, it's what Clive says in the chat exactly, it's partial fractions. So basically then we do it, and now please correct me if I'm wrong because I don't remember exactly, but I believe that what can be done is then we change this into, we take this C, we take this C out, and then from this we do something like a over h minus h1 plus b over h minus h2 plus c over h minus h3. So that's in the first case, and such a function is much easier to integrate because this is basically a sum of logarithms then. Or we can get minus mu g over rc, and this will be a over h minus h1 plus b sorry, not x, but bh plus c over h squared plus d1h plus d2. So that's the second case. And here after integrating, we again get a logarithm, and this becomes more complex. This actually turns out to integrate into an arctangent, which leads, I won't go through all the steps here, but basically if you do this, this can be all done automatically. So knowing the polynomial, knowing the coefficients, we can first calculate if it's the first or it's the second case. And in both cases, we can automatically calculate the roots and do this decomposition and then calculate all those constants. That's not that complicated. Actually, I think there is a case where my code would break down, and it is if the polynomial happened to have a double or a triple root. Because if I remember correctly, if there is a double or a triple root, then, well, technically it's this decomposition, but it's h1 in all three of those parentheses. And then if you just try to do it a over h minus h1 plus b over h minus h1 plus c over h minus h1, obviously this makes no sense because this all combines into a single fraction and it's not really equivalent. So I think then then you also have Truth Nerds writes, I think there is a special case for roots with multiplicity over 1, yeah. So then you should also have such a linear term over a quadratic polynomial, and possibly if this is a triple root, then you just have something. Then you just don't even decompose it. You just take this c out, and then you have h minus h1 to the cubed and some constant, right? So you get this, and then you need to integrate this. So those cases I don't really handle right now in the code. Fortunately, I never hit any of those cases, probably because when you get a random spline, it's rather improbable for the random spline to happen to have a triple root or a double root. But technically my code apparently is incorrect for now, so I should fix that. But yeah, basically let's copy this because, wait, is it? Yep. So let's call this 1 and let's call this 2. So for the first case, I won't go through all the calculations, I will just write the result. So p of h will be something like that. It will be p0. Let me check my notes. Okay, and this looks something like this. 1 plus a1 h minus h0 to some exponent e1. I won't even write those exponents explicitly because it's a lot. 1 plus a2 h minus h0 to the power of e2, 1 plus a3 h minus h0 to the power of e3. So that's the solution for the first case, and those constants a3, e3, and I think even h0, but I don't remember currently. Let me check in the code. So if we look, here at the pressure profile, so you can see, wait, is it here? I wanted to show you. Okay, so those are just variants possible. So we have exponential variant. It's when the temperature is linear and it's constant. There is a power variant, which is when temperature is linear and non-constant. There is this triple power, which is basically this, and there is this fourth variant, which corresponds to this second case here, and this second case here is actually P of H equals P0. Okay, 1 plus A1 H minus H0 to the power of U1, and then we get 1 plus A2A minus H0 plus B2 H minus H0 squared to the power of E2 times, and this one is just great, E to the power of some constant times arctangent of and let me check my notes so that I don't lie to you. H minus H0 divided by some A3 plus B3H. Right. Yeah. So that is what the solution for this case looks like. And when I saw e to the power of arctangent, I basically, I don't know. Yeah, I sat there confused for a while. This is not a combination you see often, but yeah, that's just the result. So I actually didn't calculate all of this by hand. I'm not that good of a mathematician. I helped myself with Wolfram Alpha, so it helped me a lot. I just entered the general form of the function, and it told me what the solution is, and then I just had to figure out what the constants are. I think it even helped me in figuring out what the constants were anyway. All of this is here in the code, so you can see that this is P0 times 1 plus A1, H minus H0, etc., etc. And this is basically a lot of crazy stuff, and then all of the constants are defined here. Yeah, and then basically if it's this, then then it calculates it as it was defined basically. And then, yeah, if temperature function is cubic, so you can see that I basically take the polynomial and check the factors, and this basically performs the decomposition into this constant, and then either 3 linear terms or 1 linear and 1 quadratic. So if we have this linear and quadratic, there is this whole calculation which I really don't remember details of. If you really want, you can go through it, and then you will see, you might be able to figure out how the constants are calculated. I just did it once and forgot about it, and that's it. It's coded here, it works, and I really hope I won't have to fix stuff here. TruthNerd says the arctangent can be expressed as a complex logarithm. Yeah, that's true. It's like a logarithm of there is I somewhere in there as well. But yeah, it's a complex logarithm, and then you have a complex argument, and then you actually get an arctangent, so that is true. But yeah, but still, exponent of arctangent looks a bit surprising. But yeah, so this is how pressure can be calculated from a single point. When you have cubic splines, you need to just solve this equation, and then you can use this to basically propagate the pressure from this set point to the boundaries of the spline, and then go to another spline and another spline, and all of this is then connected. And what I can show you is that difference. So let me close this. So here I prepared for you, so this is actually based on the 2 examples I've shown you. So the green line here is based on this linear function. So here temperature is piecewise linear, so we start here, and here it changes, and it changes, and it's straight line here again, and then it changes and it changes. It actually changes more times here than in the definition, and that's because when I output the temperature profile, I think it goes every, I don't know, every 1/10 of a meter or every 1/5 of a meter, something like that, and it doesn't, it's not cleanly at the boundaries. So basically it calculates the temperature at different points, and sometimes it doesn't evaluate it cleanly at the boundary between the two lines. So if it's slightly before the boundary and slightly after the boundary, for example here, in fact this line should be extended here and this line should be extended here, and they should intersect somewhere here. But because of how this graph is generated, you can see that. And the purple one is spline, so you can see it's much smoother. It still has some cusps here, but that's only because it's only an artifact of what I'm saying, that it's evaluated every so often. So it's just a discrete set of points, and when we connect it with lines, it seems as if it's not smooth, but it is actually smooth. Right. So yeah, so that's how defining temperature works in the simulator. Okay. Right, so I've already said everything about this. Okay. So that concludes the part about the atmosphere. So we have 3 more parts. There is viewport model, terrain model, and coloring model. Okay, let's go quickly into the viewport. So, viewport model. So the viewport model is about translating pixels into directions in space. So if we have observer at this point, the, let's say, okay, in quotes, most correct way to translate pixels into directions in space, especially when we want to have a perspective view, would be to do it like this. So we have an image plane, and let's say 0, 0 is here. So we have some point xy, right? So we have some xy point on this plane. And here, so we can imagine that the observer is at some distance z from this plane. Let me maybe draw it differently, because the way I drew this, it will be unreadable. So let's imagine that there is xy somewhere here, and that the observer is at some distance z from the image plane. So then we will say that this point xy corresponds to this direction, expressed by this vector. So basically, if we say that this is the z-axis, that this is the y-axis, and that this is the x-axis, for example, then this vector v of direction will be simply v equals just simply x and y from the image plane, and then this z, which we'll call z0, because it will be constant. It will be constant for every point. And that's it. And we can also normalize it, so we can divide this vector by its length, so that the length is 1. Usually vectors representing directions are preferred to have length 1, because then they can, it's just easier to multiply them by some factors. If you want to sum, if you want to calculate a sum of some vectors in different directions, then you just multiply the direction vectors by the respective numbers, sum them, and it's much easier if it's a unit vector, so then this can be normalized as well. But initially it can be just thought of like this. And what is this z0? Well, it can be defined using field of view, because what you define in the configuration for the simulator, if you take a look, oh, I don't have anything like that open, then let me okay, so if you take a look at how it's defined, so the view is defined by the position and altitude of the observer, so just the position of the observer, And then frame is defined by the direction in which the observer is looking, the tilt, which is basically the elevation angle of the direction in which the observer is looking. Maximum distance is just the cutoff, because when the ray is not hitting anything, we need to stop simulating at some point. We can't go to infinity with it. So basically, when the ray reaches this distance and it still didn't hit anything, we just considered that we hit the sky and the pixel is colored black. And we have a horizontal field of view in degrees, and that is what defined this Z factor. So the way this works is basically if we have some width here, so this is actually half width, right? So if we have some width in pixels, then we consider that half width divided by Z0. So width divided by 2Z0 is equal to tangent of this angle, and this angle is just the half of the horizontal field of view. So we can call it f half. Okay, and so from this we can basically say that Z0 is W divided by 2 tangent of field of view divided by 2. So that's how we can calculate it, and then we can use it to define vectors. And this way, what we get is actually a rectilinear perspective. So if there is some straight line here, if we disregard refraction and we propagate rays along straight lines, then this will actually map to a straight line here in the image. So that's what it means for perspective to be rectilinear. And if we have some object here and some object here, and they are of the same size, then actually in the image one will be larger and one will be smaller, because this way of translating pixel positions to directions automatically makes it so that the distances in the image are tied to the angular distances and not linear distances, which means that we automatically get perspective. So that's an important point to flat earthers, which always ask, and actually even Flatzoid asked me today because I posted some simulations on his Discord, and he asked me whether the simulator accounts for perspective, and I told him that yes, actually it does. And then we had a brief exchange about that. Sable Eagle asks 150,000 watt unit, so it's in meters. So I basically use SI units where applicable. Okay, so yeah. So this way we will get rectilinear perspective, but and now the interesting part, this is not how this was originally coded. And I had my reasons for that. So when it's coded like this, maybe I'll just tell you how it was originally coded and why. This will be simpler. So this is how it should be coded. So this is basically what most cameras strive to simulate. So when you have lenses, most lenses are basically most lens manufacturers are attempting to make at least not wide angle lenses, but like regular lenses. They strive to make them as rectilinear as possible, so they should approximate this, what I described here, as much as possible. But initially I did it a different way, and the way I did it initially was like this, and it was much simpler, and it also had one nice side effect. So initially the way I did it was like this. The center point of the image, 0, 0, is mapped to the angle, to basically azimuth and tilt of the camera. So the azimuth in which the observer is looking for the center point is the azimuth chosen in the config, and the elevation angle initial is chosen according to the tilt of the camera. And then every pixel, if you assume this to be 0, 0 and this to be xy, then every pixel is just azimuth equals, let's call this azimuth 0, 0 and tilt 0 is just azimuth 0 plus x times times field of, no, actually it's just divided by width. And elevation angle equals to tilt plus y times field of view divided by width again, so this the same constant. So basically now these coordinates in the image are just proportional to the angles, and then the distance in the image is also proportional to angular distance in both the vertical and horizontal direction in every place in the image, which is kind of nice. Well, it at least as long as the tilt is not large, because if it is large, then bad things happen, and that is kind of the problem. That is why the rectilinear simulation is rectilinear model is in a way superior to this one. But also this one is very easy to calculate, and the main advantage of it, and why I chose it initially, is that every row has the same elevation, and every column has the same azimuth. And now ray paths of the rays of light only depend on the elevation, and the profile of terrain under the ray only depends on the azimuth, which means when starting the simulation, and I can cache the ray shape for every row separately, and I can cache the terrain shape for every column separately. So I only need to simulate as many rays as there are rows, and I need to read the terrain only as many times as there are columns, and then I can use those values that the program remembers to basically do a kind of a Cartesian product of one times the other, and just pick pairs one from each set, and then check where the ray intersects the terrain, and then get an intersection and color the pixel accordingly. And this is much faster than just going pixel by pixel. This accelerates the program a few tenths of times. Sable Eagle says, works for small fields of view. Yes, small fields of view and small tilts. Because if there is a large tilt, then basically you're in rectilinear perspective. If you looked at the sphere so close to the equator, it just looks like this, right? So this is very close to what you will get with this. But in rectilinear perspective, if you tilt the camera a lot, it will look more like this. And this is, well, not even like this. This should even be curved. And this is not what you will get in this model. This is completely not what you will get in this model. It will be completely different. So yeah, so small fields of view and also small tilts as much as possible. But fortunately, most long distance observations, which is what I'm most interested in simulating, work with small fields of view, because otherwise you don't see anything because the objects are distant, and small tilts because you're looking close to the horizon, which is usually within a degree or so of horizontal. So both the conditions are usually satisfied, and then this is a great approximation, and the simulation is so much faster that using rectilinear doesn't really make sense anymore. But I also implemented rectilinear to be able to simulate wider fields of view, because in wider fields of view the distortions are very visible, and I will actually show it to you right now. Right, so this I can close. So I prepared this. So this is a sample view. Wait, you don't see it yet. Okay, you see it. So this is an example view. It's from somewhere in the UK. I prepared this configuration for I was going to debunk some meme where somebody claimed to have seen Mont Blanc from the UK, which is a distance of above 1,000 kilometers. So it doesn't really make sense, and I think what they mistook for Mont Blanc was just some clouds on the horizon. But that's not the point here. The point is that the photo taken was actually a wide-angle photo, which is actually also a good argument against why for why this wasn't Mont Blanc, because at this distance it would be very small, so with a wide-angle photo you wouldn't see anything. And so I simulated it, and when I simulated it using this fast generator, so I'm basically what these different approaches I'm calling generators, because basically this is the part that generates the whole image, and it decides how it will, what azimuths and what elevations different pixels will correspond to. So this is the fast generator, and this is basically this approach where every row is the same elevation angle and every column is the same azimuth. And this is what it looks like. But if we switch to rectilinear perspective with the same azimuth and the same field of view, what we get is this. Actually, this I will. It's almost the same. There are slight differences. I will tell you in a moment what that is. So we get this, and you can see that if we switch between one and the other, there is a visible difference. Because this is already a fairly wide field of view. I think it's like 69 degrees. So it's large, and the small angle approximation doesn't work anymore, and so the fast generator is no longer as accurate. And if you try to compare these two simulations to the photo, the rectilinear is a much better match to everything. Actually, initially I was wondering why I'm getting such a bad match to the photo, but then I realized this is a wide field of view. I need to use the rectilinear perspective to get a better fit. And this is quite a good fit to the original photo. And the third one, so just to give you a sense of what we're dealing with here, I've actually taken a note of how much time it took to generate these pictures. So let me tell you this. This is a picture that is full HD resolution. It's 1920 pixels by 1080 pixels. And since this was supposed to be showing Mont Blanc, I set the maximum distance to 1300 kilometers, which is a lot, and which means that when a ray hits the sky, well, it needs to be propagated for 1300 kilometers, and it needs to be checked along all this distance if it doesn't hit the terrain, which takes a long time. So the fast generator took 71 seconds to generate this image. So 1 minute and 10 seconds. Generally, full HD images take somewhere around 30 seconds, but I'm usually setting the distance to, I don't know, 300 kilometers maybe. So then it's much quicker. This one took 71 seconds. The rectilinear one took 3,883 seconds. That's over an hour. So that's the difference in speed, because for rectilinear, it doesn't hold that every row is the same elevation and every column is the same azimuth. So every pixel needs to be calculated separately, and this extends the time, well, 50 times, over 50 times. So that's the difference. But I implemented a third way. So what if we could do something like the fast generator, but then distort it to get an image more similar to rectilinear generator? And that is something I called interpolating rectilinear, and this is the third image, and you can see that the differences between rectilinear and interpolated rectilinear are almost non-existent. If I zoom, for example, on this mountain here, you can see that there are some like single pixels here, and this is fairly flat. And then if I show you this on interpolated rectilinear, you can see that it's a bit different. You don't get those pixels with small gap in the middle, and it's not that flat. You have a different top here. So there are single pixel differences, but the general shape at the first glance, it's almost indistinguishable. So yeah, and this interpolating rectilinear took, let me check, 464 seconds. So it was something like 9 times faster than the rectilinear one. Still about 6-7 times slower than fast one, but it's more bearable. So yeah. But yeah, it gets pretty much rectilinear result, and what it does is basically it first generates a grid of azimuths and elevations. It does what the fast generator does for those azimuths and elevations, and then interpolates between the pixels that it gets. So those interpolations sometimes might go wrong, and that's why the single pixel differences can appear. But most of the time it's fairly accurate and you get a good shape. And still it's pretty far. Real Sinus says offload to GPU. And yes, that would probably be a good idea, only I'm not really sure how to do that properly, because I'm not sure how to load all of this data that is needed to the GPU. But that would probably be a good idea. Right. But yeah, so that's basically how this works and how the viewport model works. So right now there is the fast model, there is the rectilinear model, and there is this interpolating rectilinear, which is basically fast but then distorted and interpolated so that it emulates the rectilinear one. And it works fairly well, as you can see. And I also wanted to show you, and I will show you what the difference is between the two in the case of a small field of view. So let's take the famous Blackpool photo that's generated with the fast one, but unfortunately I started generating the rectilinear one like half an hour before the stream, and after half an hour it was still at like 53% or so. And yeah, this program takes up 100% of my CPU, so I wouldn't be able to stream with it running, so I had to cancel it. But I have the interpolating rectilinear, wait, not this direction. So this is interpolating rectilinear and this is fast. And as you can see, the differences are again almost non-existent. And those are between fast and interpolating rectilinear, which means the fast one, which isn't rectilinear per se, for small fields of view, and you can see that it is small. You have from 352 to 357, this is 5 degrees horizontally. So this is a small field of view and it works fairly well in this case. Of course, it's a bit rougher at the edges because of all the interpolations, which can sometimes go wrong. But in general, it's fairly good. But as you can see, for such small fields of view, it just makes no sense to use the interpolating rectilinear because it's slower and it's less accurate. So the fast one is the go-to for such applications. Only if you have a wider field of view, it's a good idea to use the interpolating rectilinear. Actually, I can show you something. Something more, which I didn't plan initially, but I think it would illustrate this nicely. So one thing that the fast generator will never show you is the curvature of the horizon. No matter how high you put the observer, the horizon will always appear as a straight line for the fast generator, because the horizon is at a constant elevation in every direction, which means it corresponds to a single row in the image, which means you will never see the curvature of the horizon, but you can see the curvature of the horizon in the rectilinear one, and I just want to show you this. I have a nice... So I've tried reproducing a photo from the ISS, and as you can see, this is ISS passing over Europe. You have the Alps here are the Tatra mountains, so this here is Poland, this is somewhere here Slovakia, this is Lake Balaton, I believe, in Hungary, and you have Italy here, and further away actually you might be able to see some of the Pyrenees, I believe. At least that's what the simulation shows, because you can see the Alps here, you can see a clear contour of Italy, Croatia, you can see mountains here, and then you can see those are the Pyrenees. It would be Spain right there, but it's beyond the horizon, and here we have France. So yeah, so this had to be calculated with the rectilinear simulator. I don't remember if this was rectilinear or interpolated rectilinear. I believe it was the pure rectilinear, so it probably took some time to do this. But yeah, if I did it with the fast generator, the curvature of the horizon would be imperceptible, wouldn't be there at all, because it would correspond to a constant elevation. But yeah, that's what it looks like. All right. Only 2 more things to go. So maybe I'll finish it today. My wife will be angry that I'm sitting so long and streaming for more than 3 hours, but I really want to give you a complete overview of all of this and just close this chapter and have the recording of this stream as reference. I might cut it later and combine it into some kind of a video, or just now that I know what I was talking about, maybe I will be able to make a shorter video that covers the main points. But yeah, as you can see, it's really a lot to cover. Okay, so let's go and talk about the terrain model. Oh, Truth Nerds says that there is very little branching and high parallelizability, good for GPU. One downside is most graphics cards only give you a single precision. Probably single precision gives good enough results. Yeah, that might be. I'm kind of going for doubles by default, so that's the main reason why I use doubles. It's not that I performed like a very thorough analysis whether I need them. So it's quite possible that single precision numbers would work, although they have something like, what, 7 or 8 significant digits? Like decimal significant digits, if I remember correctly. So for the distance of the order of 1,000 kilometers, well, that might be single meters of inaccuracy, but that shouldn't be much, right? I don't think that anywhere here single meters matter at those distances, so it's quite possible that it would be enough. I would have to rewrite it using single precision and see if that helps the performance, and second, if that doesn't change the results too much. It might be a nice project for optimizing this stuff. And for GPU, I would first have to really figure out. I'm not really experienced in offloading stuff to GPU. I did manage that in my black hole simulator, but that was really like a real-time something that actually worked with an actual texture. So I'm not sure how I would go about it, and I don't think you can write Rust for GPU, which would be sad. I like writing Rust, and I don't really like writing C or whatever is needed to write code for the GPU. So yeah, but might be also a nice idea for a project and for making it more efficient. Anyway, let's talk about the terrain model. There is really not much to discuss there. So basically how the terrain works is there is a website. Do I have it here? Oh yeah, Earth Explorer usgs.gov. So this is a website where you can actually find many different kind. Oh, okay, I blocked a lot of JavaScript and it again. Perfect. So you can get many different kinds of data for basically the whole world. One of the, so if I just, okay, maybe not, clear coordinates. So maybe I'll just show you like some small rectangle and data sets, and here there are digital elevation data sets. So what I'm usually using is this SRTM 1 arcsecond global. And if you look for it, then you get, you can download tiles, and every such tile is 1 degree per 1 degree. So it's 1 degree in latitude per 1 degree in longitude. So you need multiple such tiles to cover some significant area. And what the program does, it basically loads these tiles on demand lazily. Initially it was just coded, it would just load all the tiles that it would detect in the folder that it is pointed to. Do I still have this open somewhere, or no, I don't. Anyway, in the config you can specify the directory for the terrain data, and the program will just first go through all the files, and it will try to detect all the terrain data files in the folder. Yeah, and then initially older version would do it the way that it would just load everything into memory and then work on that. But then it required me to always select the precise tiles that I will be using for a specific simulation instead of keeping them all in one folder. So eventually I drop them all into one folder and load them on demand. So basically whenever what it does, it goes through all the tiles and it indexes them by latitude and longitude. And then whenever it needs to check particular coordinates on the surface, if it doesn't have the particular tile in memory, it just loads it from the disk and then checks. And if it's not present, it just assumes that it's C over there. So if you don't have a tile for some area, it will just assume the C. Right. And those tiles, as I said, they cover 1 degree per 1 degree squares. And they cover them with 1 arcsecond resolution, which means they have 3600 points in either direction. But that also means that the points of elevation are separated by about 30 meters, if I remember correctly. Which means that on smaller scales, you have point, 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 and nothing in between. So if the ray lands somewhere here, we need to do some calculation because we have the elevation only at those points. So what I'm doing in the code is just bilinear interpolation. So I interpolate this linearly, I interpolate this linearly, and then we get the 2 points here, and then we interpolate this linearly, and we get the elevation at this point. So this is a very rough approximation, but since again at distant observations the details at this scale don't really matter that much, it's usually good enough. And when it's not good enough, then well, tough luck. I never really attempted to code anything better, and that's usually enough for proving a point. And that's just the simplest way of interpolating. This actually, if you think about it, it might seem that since this is doing a linear interpolation here and linear here, and then again linear, it might seem that this should be always a plane, but it's not true, because even if you think about it, 4 points are not necessarily coplanar. So it might be that there isn't even one plane that passes through all 4 points. So in general, it's a more complex shape. For example, it might be like parabolic hyperboloid or hyperbolic paraboloid, whichever way it's called, I don't remember. Basically, it's the shape that you have parabola, and basically it's parabolas upon parabolas. And it's called hyperbolic because if you take a slice, then here you get a hyperbola, for example. So you can get such a shape. Actually, if you investigate, it turns out that such a shape, I think it's called hyperbolic paraboloid, it actually can be decomposed into infinitely many straight lines. So that's a bit non-intuitive, but it's true. And the same goes for a single sheet hyperboloid, which is basically a hyperbola that is rotated around its axis. So such a shape also can be composed only of straight lines, can be decomposed into straight lines. So in theory, probably you can get it using this bilinear interpolation. But yeah, that's not that important. So that's really everything that can be said here. The program interpolates between the 4 closest points, checks the elevation, checks it with the ray. If the ray intersected it, so it might be that at 2 subsequent steps, so we have the ray, and it's going away from the observer, and we have the ray here, and we have the ray here, right? And it went from this point to this point, and then we have the terrain, and the terrain went like this. So here the ray was above the terrain, and here the ray is below the terrain, which means we had an intersection somewhere in between. And then what the program does is, again, it does a linear interpolation, and it finds the intersection, assuming those are connected with straight lines. So that's how the intersection point is calculated. And then the position and elevation of this point is taken, and it is used for further processing. So that's how the terrain works. And final thing is coloring, so that's the last part I wanted to cover. So basically we have covered everything. So we have an image, it's decomposed into pixels. For every pixel it gets a direction, in every direction it traces a ray. Every ray is then compared to the terrain. When it intersects, we calculate the intersection. We have the intersection, so for every pixel in the image now, with what we discussed, we can calculate an intersection of rays of light with the terrain for every pixel in the image. What is left is to assign colors to those pixels in the image, and that's the last part. So what data do we have about a pixel? We have its latitude, longitude, elevation. We have its distance from the observer. We have actually the length of the light path itself, so it's not the same as the distance from the observer because the light path might have been going up and down, so it might be a bit longer than the distance along the surface. And this length of the light path is used for one specific application, and that is fog. So you can actually add fog to the image so that the distant objects are a bit more fuzzy, but it's not implemented very well, and it's not a very good fog. So I usually just turn it off. It doesn't really help anything, but it is there if someone wants to play with it. Right. So we have those. So we obviously have something like what direction the observer looked into. So we have the elevation angle and azimuth, and we can use all this data to color the pixel. So the initial implementation I had used this data, and the way it colored the pixels, I will show you. It colored the pixels based on the elevation and distance. So basically distance affected the saturation of the color, so the more distant the object was, the less saturated the color. And elevation, I believe it just went from green through red to something like black. I don't remember the exact details, but I have a simulation using this old coloring scheme, and it looks like this. So this is a view of Mount Denali from Anchorage in Alaska, and you can see that, well, it doesn't look that well, especially since I was showing you some of images I generated with the newer coloring scheme already. So you can now compare what that looked like to what this looks like, and as you can see, it wasn't very pretty. And if we compare it to the new coloring scheme looks like this. I will talk about it in a moment. But you can see that, for example, here is some peak that here is almost invisible. It is here. If we look closely, it is here, but it's almost invisible, and it's really hard to see any detail in this image. In this image, it's much easier to see some details, some ridges on the mountain here. It's pretty much invisible. So yeah, so I very much prefer the new coloring scheme now, and whenever I'm generating some simulations, I'm using the newer scheme. So how does it work? Well, besides the elevation, it uses elevation for the color again, so it tries to simulate what you could expect. So the lowest parts are green, like grass could be, and then I think it goes through yellow to gray, as in rocks, and then to white at highest elevations, as in covered in snow. So it tries to kind of simulate realistic colors this way. But also you wouldn't get this shading with just elevations, distances and stuff. So it needs also another piece of data, and that is a normal vector to the surface, which is actually quite easy to calculate when you already have the intersection point. So what I'm doing to calculate the normal is, well, first I figure out where the north and east are. So let's say they are here. Then I read the elevations for 4 points that are at small distances from the central point. And this gives me a numerical estimate for the gradient of elevation in those two directions. So I can basically get what the slope is in these two directions. So I can get two vectors that I can get two vectors, an eastern pointing vector and northern pointing vector, that in the vertical direction, in the z direction, basically represent the changes in elevation. And then I just do a cross product. When you do a cross product, you will get a vector that is orthogonal to both of them, and that will be the vector orthogonal to this part of the surface. And this cross product is what I use. Then basically I have this, let's say this is the surface, I have this normal vector, and then I have light falling from this direction. So I can take this angle. This angle can be calculated via a dot product. So I can take dot product of the lighting vector and the normal vector, and this when those vectors are unit vectors, so that is again a reason to use unit vectors for directions. This dot product just gives me the cosine, well, cosine of this angle if this vector is not directed this way but this way. So if I take the negative of the lighting vector, then I can get the cosine of this angle. And then, if I remember correctly, I set the brightness of the surface to cosine squared of the angle, something like that. I think that's the general practice when calculating lighting. That's also what 3D graphics engines do. Like if you use lighting in OpenGL or something like that, it also does a calculation like this. So yeah, so that's pretty much it. And then you get a surface that is nicely shaded, and you can see all those ridges, nooks and crannies and stuff like this. And it looks much nicer. So yeah, so that's the simple recipe for that. And I think that's it what I wanted to say about coloring. Yeah, that's how this works. There is, I think, one last thing I wanted to show you, but I didn't make a note on it. Oh yeah, yeah. So that's, let's say, a bonus. So, did I show you this? Yeah, I think I showed you. Oh no, I didn't show you this one. Okay, so I also prepared an example of different shape models, Earth shape models, on a photo, on an example of a photo. Let me show you. Okay, let me see. Okay. So this is actually a simulation of a view, of the famous view where a photographer photographed mountains from over 400 kilometers. It's in France. I think I won't pronounce the names. It's Pic Gaspard. I think I'm probably butchering the pronunciation. So Pic Gaspard is one of those mountains here. It's 440 kilometers from the observer, which is at some other peak in the Pyrenees. And that name I have no idea how to pronounce. Anyway, somebody posted this, so this is the photo that somebody posted. This actually, Pic Gaspard is not in this photo, it's somewhere to the left. Yeah, exactly, Truth Nerds wrote the name. I don't know how it's pronounced, I don't know French, I'm sorry. I only know that that French people pronounce stuff weirdly, so unfortunately when I see written French I have very little idea how to pronounce it, so I won't even attempt this one. Anyway, it's some other peak. Pic Gaspard is somewhere to the left here. This one is, I don't remember the name. Some started with a B, that's what I remember right now. Anyway, someone posted this photo on Flatzoid's Discord and said that it's obviously flat. So I countered with the simulations. This is the simulation on a globe, so we can see that it reproduces pretty much the view from the photo. And if we go for flat, then we get this. And I also prepared the different models. So this is the flat spherical model, which is observer-centric azimuthal equidistant. This is, of course, spherical. This is the flat distorted, which, as you can see, shifts everything to the right, but mountains more than the things that are closer. And there is the azimuthal equidistant, which somehow, I think, no, it's shifted even more to the right, so the headings are completely all over the place. So yeah, so those are the 4 models. But yeah, Flatzoid started countering that my simulator definitely doesn't account for perspective, and when I told him that it does, he started asking, but how can you prove it, etc. So I got an idea. Since I can also add objects to the scene, I decided to add some cylinders. So I decided to place some cylinders to the left of the line of sight, a cylinder every 50 kilometers, and every cylinder 3 kilometers in height. And I will show you right now what it looks like. And this actually nicely shows that the simulator actually does account for perspective. So if any flat earthers are watching, please take note. So that is what it looks on a globe. Each and every one of these cylinders is 3 kilometers tall. So the top of it is 3 kilometers above sea level. By the way, this purple line represents eye level, so this is horizontal. So you can see that the horizontal intersects the first pole here, and every other pole doesn't even intersect horizontal, because basically they are dropping on there is this drop of a curved surface. So that's what we expect on a globe, and we see this perfect curved line of the tops of the cylinders, which shows A, that this is on a spherical surface, and B, it shows perspective because every subsequent pole is smaller than the previous one. And this, and this is what it looks like on a flat simulation. And now you can see that it, again, you can see the eye level. I don't know if you can see it, but the horizontal is here, the eye level, so to speak. And this is actually without refraction, so that we can, so everything is rectilinear. So we can see that those poles, those cylinders, nicely appear to converge here on the vanishing point in the center part of the horizontal line, but somehow it looks completely different from the photo. But yeah, it shows that perspective is taken into account. Those poles clearly are smaller in the image when they are further, and if you look at them, well, you can see the bottom of this pole and you can really see the bottoms of those poles, but if you look at those middle 3, they start at the sea, so you can see the whole 3 kilometers of them. And you can see that this one is roughly 2/3 of this one, which is to be expected because this one is 100 kilometers from the observer and this one is 150. So 1.5 times further, 1.5 times smaller. And this one is roughly 2 times smaller than this one, which again makes sense because it's 200 kilometers. And again, this horizontal intersects every pole at the same height. If I actually textured those poles and added some kind of a scale on them, you would be able to see that each and every one of those poles is intersected at the same height, and that's observer height, and that's roughly, I guess 2,800 meters or something like that, or 2,700. So yes, perspective is taken into account, and this shows precisely what should be seen if the Earth was flat, including the terrain, and that is not what we see on photos. Alright. So yeah, so that concludes what I had for you today. Almost 3.5 hours, and I think that is enough. Clive Wells, don't forget the vanishing zone and the RC. I don't even know what is RC, but vanishing zone, yeah, definitely. I probably should basically edit this in some kind of an editor and cut out like a strip out of here, because this is the vanishing zone and everything vanishes, right? All right. Alright, so I hope, yeah, I hope that was... Oh, Rayleigh criterion, of course, yeah. I should have known, yeah. Yeah, this simulator does not account for the Rayleigh criterion. It has theoretically infinite resolution, but of course the resolution is limited by the resolution of double precision floating point numbers, and it's limited by the resolution of the image. Oh, okay. Yeah, thank you for coming. I see Real Cygnus is thanking, Truth Nerds is thanking me. Thank you. It's awesome that again, it's really awesome that I wasn't talking to myself, and I hope you found this useful somehow, and that yeah, that it wasn't too boring and too mathy. But I guess that everyone who came here really knew that they should expect a lot of maths, and maybe some of you even came here for the math. So yeah, all right. So yeah, again, thank you, and yeah, I'll be finishing. It's almost midnight here now, so it's time to rest, I guess. Yeah, so I don't think people like Gary or Flatzoid will watch the entirety of the stream, but if they do, maybe they will take something out of it. I would hope so, but I don't expect too much. Alright, yeah, again, thank you everyone. Thank you Dora, thanks Clive, and thanks Real Cygnus, thanks Truth Nerds. And if I'm missing someone, apologies, but thank you everyone who was watching. See you in another one. Oh, PT is here as well. Good night, thank you. Bye bye.